So, good afternoon, everybody. My name is Christoph de Lago, and it's a real pleasure to welcome you all here at the Erwin Schrödinger Institute for today's award ceremony for the ESI medal. Before we start with the whole ceremony, I would like to remind you of the safety precautions that we have here at the ESI. So only people who are vaccinated or tested or have recovered are allowed to enter the building. In the hallways and the stairways, please wear your mask. In the lecture hall, you can take off the mask. The University of Vienna recommends to wear the mask also when seated, but it's okay if you take it off if it's easier. So, welcome. This is a really nice occasion. We are going to award the ESI medal to Elliot Lieb from Princeton University. Very proud that he is the second awardee of the ESI medal. Let me extend a particularly warm welcome to Vice Rector Regina Hitzenberger, who will later give a few words. She's also a physicist, so I'm particularly happy that she is here today. I would like to welcome also the members of the Scientific Advisory Board of the ESI, who play a very important role in for the medal, because they are those who select the recipient of the medal. I would like to welcome, if they are online, the deans of the Faculty of Physics and Mathematics, Martin Falli for Physics and Radu Bot for Mathematics. And it's a particular honor that last year's awardee of the recipient of the ESI medal is here with us today, Anton Alexeyev from the University of Geneva. I think Anton wasn't here last year, so he is late for 1 year. So please, a round of applause for him. It's really great that you made it today. I'm really glad that you are here with us. And finally, of course, it's great that Elliot Lieb is with us today. Unfortunately, he couldn't come to Vienna for this occasion, so he follows from his home in Princeton, and he will also give a talk. So welcome everybody. So I would like to ask Regina Hitzenberger, Vice Rector of the University, to say a few words, please.
Thank you, Christoph. Well, dear colleagues, it's really marvelous to be here, to see so many known faces from the old time, also the ESI medalists of last year. It's my pleasure to welcome you here at the University of Vienna, to welcome the virtual audience to this ESI award ceremony in the name of the University of Vienna. Welcoming you is one of the best parts of my job. Of course, I've known the ESI since the time that I was Vice Dean of Physics. I always had to do with infrastructure. And I remember this room from my first semester. It was because this was one of the lecture halls of the former Mathematical Institute at that time. So the ESI, well, as you know, it was founded in '93 as an independent institute to strengthen collaboration between physics and mathematics. And when the question came, what would happen to ESI when those independent institutes were under discussion at the ministry, the University of Vienna was very glad to welcome the ESI as a research platform. And since that time, the ESI has been one of the gems in our research portfolio. The ESI is truly international. I got the numbers. Before Corona, there were about 1,000 people every year coming here, working together, talking together. well, last year everything was not in presence. Now we are really happy to be able to have some things such as this award ceremony in presence. Let's hope we will be able, as a scientific community, to go back to meeting in person. Scientific collaborations are international. The scientific community is international. I was asked, should I say a few words about the University of Vienna for those who do not know us? We are the oldest university in German-speaking countries. 1365, so we are 656 years plus a few months old. And at that time, actually, the scientific community was truly international. International at that time meant Europe. And today, it's still truly international. University of Vienna is international. We have about a third of our faculty are international. About a third of our students are international. As a university, we are big, just a few numbers, about 10,000 employees, 90,000 students, so 100,000 human beings are the present community of the University of Vienna, but of course all those who pass through our gates also are members of this community, and international collaboration, international research is very, very important to us. And the ESI is as I said, one of the gems in our, I'm not saying crown. So I'm very pleased to be here to welcome you, and also to, well, here I have to turn around to see Elliot Lieb. Today is the recipient, this year's recipient of the ESI medal. A highly renowned scientist, one of the world-leading mathematical physicists, and we are proud to say, as University of Vienna, a friend of the University of Vienna and a friend of the ESI, and it's very, well, it's a pleasure and also an honor for the University of Vienna that Elliot Lieb accepted the medal and accepted the award. It's marvelous, and well, you heard my sigh. As Vice Rector of the University of Vienna, my job is mainly business and not pleasure. It would be a pleasure to stay here and listen to the talks. I have to leave again. It was just a short visit to come here, but I really wanted to do this. I really wanted to welcome you all, and I envy you a bit because you now have a highly interesting afternoon. And I have to go back to management, which also is interesting sometimes. So welcome, all the best, have a very nice afternoon. And again, congratulations to former year's ESI medal recipient and to this year's ESI medal recipient. Thank you very much.
Thank you. Thank you very much, Professor Hitzenberger. We now let you go back to your duties. Somebody's got to do the dirty work. We infrastructure. So thank you very much for coming and for for your kind words. It's very nice to hear that the rectorate appreciates the work that is being done here at the ESI. Thank you very much. Thank you. So I hope that you are aware that this is a historic moment. Because here in Austria, we say that if something happens twice, then a tradition is started. So you are witnessing now the start of a tradition, and I very much hope that this tradition will continue for many years. Now, as Professor Hitzenberger said, these are weird times. These are weird times, of course, also for the Erwin Schrödinger Institute. Last year, we did the medal ceremony as a hybrid ceremony, and I was hoping, So with some people attending in the lecture hall, some people taking part online. And I was hoping then that the next one will be a regular event where all the people would be in the lecture hall. And in particular, the medalist would be in the lecture hall, but it happened differently, right? So we are still in the middle of a pandemic, and right now the numbers are increasing very dramatically. In a sense, we are lucky that this happens now and not 10 years ago, because we have the tools now to make such an event possible, to be able to stay in contact. This is one of the main missions of the ESI, to foster scientific exchange. And due to the pandemic, so before the pandemic, we had about 1,000 visitors coming here to the ESI physically. Due to the pandemic, we were forced to move to virtual space. This was a steep learning curve for the ESI, but also for the entire community. And it will be interesting to see how this evolves. I'm afraid that we have started another tradition here as a community, namely that some of the communication will continue to be virtual. We will see how this will develop, but I don't think that we will return to our old mode of operation, and maybe we shouldn't. So let's make the best out of it, and so let's just say it's good that we are able to have this meeting here with so many people attending from outside, and also people delivering talks from other places in the world. So since not all of you attended last year's medal ceremony, perhaps I should explain a bit what the ESI medal is and why we created it. So the discussions for the ESI medal started about 3 years ago in the ESI Collegium and in the ESI Scientific, also in collaboration with the ESI Scientific Advisory Board. And the idea was to create a prize to recognize outstanding achievements in mathematics and physics, and in particular at the interface of the two fields. And of course, the idea is also to strengthen the ESI community, to make the ESI more visible internationally as an important meeting place and research place in physics and mathematics. So we started this, we came up with some rules. If you are interested in the rules for the ESI medal, you can look them up on the ESI webpage. Some people are allowed and encouraged, of course, to submit nominations, and these are the organizers of thematic programs, former members of the ESI Scientific Advisory Board, former directors of the Institute, and also previous medalists. They can submit a nomination, and then the Scientific Advisory Board selects the winner. And this year, the Scientific Advisory Board selected Professor Elliot Lieb from Princeton University. Maybe you can make Elliot's picture large on the screen so we can all see him. Very nice. You look good. And you have a very good camera, I think. Excellent. So this year's winner, as I said, is Elliot Lieb. He is one of the leading mathematical physicists in the world. I think it's not an exaggeration to call him a scientific giant. The speakers today will give more details about the life and the work of Elliot Lieb, but let me just mention that he really worked in a wide range of fields in statistical mechanical models, particularly analytically soluble models. He made them soluble. One can say he worked on density functional theory, the stability of matter, quantum electrodynamics, the second and the third law of thermodynamics, so really a wide range of topics that he worked on in his very long career. I looked up yesterday that his first paper was published in 1955. So this is a career that spans, well, close to 70 years now, and is still going strong. I would like to emphasize that the Easy Medal is not a prize for a life's work. It's a prize for recent work. So if you look up the statutes of the Easy Medal, you will find that this is mentioned explicitly, that the Easy Medal is given for work that is done in the last 10 years. So I think this is really amazing. I'm a computational physicist, and I think you can do wonderful things with computers. But I have an immense admiration for mathematical physicists, not because what they do is difficult. Elliot Lieb makes it look easy, but we know it's difficult. But because these are really, this is knowledge we can work on. This is for eternity. This is something that we know for a fact. And this is great, and it is really wonderful that this prize went to Elliot Lieb. He's a great scientist, but he's also an old friend of the ESI and a supporter of the ESI. He was on the scientific advisory board for many years, and he has visited the Schrödinger Institute very frequently. I learned that there was, in the year 2002, a symposium for Elliot's 70th birthday. And it's interesting that the speakers of the first session of that symposium are identical to the speakers that we have this afternoon, namely Robert Seiringer, Philip Solovey, Jakob Yngvason, and also and Elliot Lieb. Actually, but in reverse order. The order was reversed back then. So, and the titles are also different. I checked. Some people make a career out of the same thing, repeating it over and over again. Not in this case, of course. So it's really great that we are here today and can celebrate the ESI Medal for Elliot Lieb together. So before we move on, and I give the word to Robert Seiringer, let me just explain what the program will look like. So we will have a talk by Robert Seiringer, and then by Philip Solovey. Then there will be a short break. After that, Jakob Yngvason will give the laudatio. And then we will hand over the prize, virtually. And we will send it by mail, so at some point you will receive it. And there will also be some music. Normally, we would do a reception, but in view of the situation, we decided not to do that. Okay, excellent. So I would now like to ask Robert Seiringer to give his talk. Please come to the podium. While you set up here, I will briefly introduce you. You are also an old friend of the ESI, I might say. So Robert is actually was a PhD student here at the University of Vienna, working with Jakob Yngvason. After that, he did a postdoc at Princeton University, I think working with Elliot Lieb. After that, he went on to be a professor at McGill University. You were also a professor at Princeton at some point.
I was assistant professor there, yeah.
And then a professor at McGill before he returned almost to Vienna. He is now a professor at the Institute of Science and Technology, Austria. And we're very much looking forward to your talk. Please.
Okay, so good afternoon. Good morning, Elliot. Let's say I'm impressed you managed to put on a tie already that early in the morning. Good morning. So it's of course a pity that we don't have you here live in Vienna, but Christoph has mentioned the tradition, so maybe we can make it a tradition that the medalist shows up here always a year late, right? So in any case, hopefully, Elliot, we can welcome you here in Vienna sometime soon again. So here's the title of my talk. Let me see how this works. I can move this around here. So I will talk about recent mathematical results on density functional theory, and everything I'm talking about today is based on joint work with Mathieu Lewin and with Elliot. And let me start, since at the end I will surely run out of time, let me start by congratulating Elliot on the ESI medal. It's of course very well deserved honor, and I must say it's been a great pleasure working with you on, well, these and many past projects, and I'm looking forward also to many future projects still to come. So let me start with sort of setting the stage. It's basically, I'm going to talk about simple ordinary quantum mechanics, basically atoms and molecules. And in the simplest possible setting, where one just considers the nuclei as basically fixed simply because they are much heavier than the electrons, the relevant Schrödinger equation to be solved is written here on the board, right? So I'm thinking of having fixed nuclei, right? There could be an arbitrary number of them. I call it M. So they have some locations, R1 to Rm in space, and they might be different nuclei, right? So they have different charges, say Z1 to Zm. So I denote by V the Coulomb potential generated by these nuclei, right? So that's the Coulomb potential at a point X. It's just the sum of the inverse differences of X and this Rm multiplied by Zm, right? With a minus, that's the attractive Coulomb force, right? So all the parameters of the system I'm talking about are basically encoded in this function V, right? There might be many different physical systems. You could describe a solid, you could describe an atom, you could describe a very complicated molecule. It's all sort of included in the choice of basically how many nuclei you have and what kind and where they are. Now, the dynamical variables are the electrons, right? And I'm thinking of a system of n electrons. And then the Schrödinger equation here, you can abstractly just write it, right, as an eigenvalue equation for the corresponding Hamiltonian, which is written down here, right? So it has the usual form. So there's a sum 1 to n for the n electrons. Here is the kinetic energy, just minus the gradient squared with respect to the electron position xi. The electrons see the force, right, generated by the nuclei. That's exactly this potential I defined up there. And then the electrons interact themselves with each other with Coulomb forces, right? So this is the Coulomb potential here for the Coulomb repulsion between the electrons. And of course, I'm choosing sort of standard units such that the most of the constants that normally appear are set equal to 1, right? So in particular, sort of the only parameters, as I already mentioned, are really in this potential V. Everything else is sort of universal, right? And now, in principle, so if you want to now understand, say here, the behavior of this water molecule, right? What you should do is you should solve this equation, and maybe actually, strictly speaking, since a priori you don't know where the nuclei are, you may actually also have to do still an optimization over the position. So if you imagine that you compute this energy, right, the eigenvalue, say the lowest eigenvalue of this Hamiltonian, this is a function of all these nuclear positions. And at the end, you may want to minimize or find stationary points of this energy with respect to the nuclear positions. And for that, of course, you also have to add the corresponding repulsive Coulomb energy of the nuclei. Okay. But actually, this will not play a role in this talk here for me. So to say the nuclei would just be fixed wherever they are, defining this potential V. So this is in principle the setting. Once you can do that, right, you can solve all kinds of important problems. But in practice, this is not really possible as soon as n is not very small, right? So maybe if n is 2 or 3, this can be done numerically at least. But as soon as n is of a large size, this is simply impossible, basically because of the exponential scaling with n. I mean, the problem is in any case infinite dimensional, but in practice, of course, one can truncate and one have sort of a finite dimensional setting, but that dimension will grow exponentially with n. And as soon as n is not very small, that means it's in practice completely intractable to actually solve this equation, even numerically. Right? So this is one of the problems. The other is actually maybe more technically the fact that the wave functions here to look at, right, sorry, where's the cursor now here? Right, so these functions, they have constraints, namely they are antisymmetric, right? So that's sort of determined by nature. The fact that the electrons are fermions means that you have to work with antisymmetric wave functions, which complicates the numerics, for instance. So therefore, in practice, this is not what people do, simply because they can't do it. They can't solve this equation. So in practice, what has turned out to be very useful is a density functional theory. And so let me just give a very brief sketch of the, I think, at least the mathematical aspect of the idea behind density functional theory. And that's basically to try to express, sort of to formulate an energy minimization principles only in terms of the density, right? A priori, we have these wave functions, which are functions of n variables, right? And you should think of n being large, and that's the problem. It's difficult to calculate. Now, given any n particle function, you can compute what is called the density, or the one particle density, which is just what you get if you integrate out n minus one of the variables, of these n variables, right? And the usual normalization is that you multiply by n, or you could also say you have n possible ways which of these you to integrate out, but since I assume psi to be antisymmetric, right, it doesn't matter which one, so I might as well just integrate over x2 to xn and then multiply by n. So this is called the density. And strictly speaking, there are some spin variables, right, because the electrons carry a spin a half. I would just suppress this in my notation for simplicity. So I will just sort of say pretend that there is no spin, or at least it's not explicitly written in the notation. Now, if we want to compute the ground state energy, say, right, the lowest energy of the system here, that's the infimum of the spectrum of the Hamiltonian. So the variational principle tells us that we can just pick any function we want, right, any psi, normalized, of course, and we minimize the expectation value psi h psi that gives the ground state energy. And one can now immediately obtain sort of a density functional version of this. So this goes back to Levy and Lieb, and is now known as the Levy-Lieb functional or formulation of the ground state energy, by simply saying that instead of minimizing directly over all psi, you could also first fix a density rho and minimize over all psi that have this density rho, and afterwards you minimize over rho, right? So this is obviously the same thing. Now, the advantage of thinking of it this way is that sort of all the parameters in the problem, which are in this potential, right, there's actually very easy to write out what the contribution to the energy is, because it really only depends on rho, right? Because the potential is a one-body potential, so it only sees, so to say, one electron at a time. If you compute this expectation value here, you always integrate out n minus one of the variables, so naturally you only see rho. So the expectation value of the v part, so to say, in the Hamiltonian is just the integral of v times rho. So that's trivial. That's not true, of course, for the other two terms in the Hamiltonian, for the kinetic energy and for the Coulomb repulsion here. Okay, so for those, you really have to do this minimization, minimizing overall psi given that rho. And that expression we call the Levy-Lieb functional. It's simply defined this way, and it's a universal object, right? Because it doesn't depend on anything. There are no parameters in there. I mean, it depends on n if you want, right? But it's basically, even n you can think of as a variable, because you can pick rows for different, the integral of rho is n, so that's also encoded in rho. So it's a universal fundamental functional of the density rho. So that's sort of the fundamental density functional, if you want. It's defined on all densities, right? So that means positive functions that integrate to n. And actually for regularity, basically for this to be finite, you need that the square root of rho has a finite gradient norm. So it's not difficult to see that any psi actually that has a finite energy here will have a density in this set called Rn. And actually what Elliott proved in a sort of fundamental paper in 1983 is that the reverse is also true. So given any density in this set, there is a psi with finite energy that has this density. So in other words, the domain of definition for this Levy-Lieb functional is exactly this set. It's very simple to describe. It's exactly this set Rn. Okay. And this paper, by the way, in 1983 by Elliott, I think it's called Density Functionals for Coulomb Systems. It's a truly marvelous paper. It's very nice to read. So if you haven't done it, I can only recommend studying it. So now this is just sort of a reformulation in terms of density functional theory. Of course, the problem is that this is completely uncomputable, right? There's no way we will ever compute this functional, because computing this functional basically means solving the n-body problem for all possible external potentials V, right? We usually cannot solve it for one even. Solving it for all of them is sort of equivalent to computing this functional. So this is certainly not computable, but I think in practice, basically what people do is they try to come up with good approximations of this functional. And this works actually amazingly well. And I'm not an expert on this at all, but if you just look at sort of say this field of density functional theory in quantum chemistry, I mean, actually applied really computing things, it's truly amazing what is being done there. And I think it's sort of based on this principle and of course a very clever approximation of the actual functional, which nobody will be able to ever compute. So one of these approximations is actually one of the topics of this talk that I would like to explain. And I think it has been called the mother of all approximations, because I think it enters in one form or another in all of these approximate density functionals. And that's sort of a principle of locality, that somehow the energy at a given location should somehow only depend on what the density is at that location. That would be sort of a strict locality. And so this will, of course, not be strictly true, but it should be almost true, at least if the density is sort of rather slowly varying. And this is called the local density approximation. So here's just a sketch. Basically, we have what you have in mind. I start with the picture down here, is we have a density that is not wild. It's sort of rather smooth and slowly varying. So we can think of sort of dividing space up into small cells, and we think that in every cell, the density is roughly constant, right? That locally you have a homogeneous system. And then if that's the case, you would expect the following, that if you look at this Levy-Lieb functional, it should roughly be local. Well, actually, it will never be local, but there's a sort of a trivial non-local term, simply having to do with the long-range nature of the Coulomb interaction. You would certainly expect a term like this. This is just the classical Coulomb self-interaction of a charge distribution given by rho. Right? After all, rho is the charge distribution of the electrons, right? So naturally, there's a classical energy, so to say, associated with it, which is not local, but it's simply the Coulomb energy of this classical, or even of this charge distribution rho. So this term should be there, but sort of aside from that, you expect that the energy should be roughly local. Strictly local would mean that it's simply an integral over space of a function that depends only at rho at this point x, right? So this would be a perfectly local functional. Of course, this cannot be strictly true. That's the approximation sign here. And what we basically set out trying to prove is, or to quantify to what extent this is true. Okay, so basically, what we were trying to do is to look at the difference between the left and the right-hand side and somehow show that it's small if rho is suitably slowly varying. Okay, so this would be a rigorous verification, if you want, of the local density approximation. And in fact, next slide has already a theorem to that extent. Sorry, it looks a bit technical maybe, but I will try to walk you through this and explain the main result. It's basically, right, as I said, looking at the difference, right? So here we have find the cursor here. Here we have the Levy-Lieb functional, right? Actually, there's a tilde on it. I'll comment on a second why there's a tilde. We subtract what we expect this to look like if rho is slowly varying, namely it should on the one hand be the Coulomb energy associated to the charge distribution rho, and there should be the local term. I will explain on my next slide what this F is, but it's basically, I mean, it's sort of clear what it should be. It's sort of the energy per unit volume of a homogeneous system at density rho. Okay, so there's this local function f of rho integrated over space, and then we claim this should be small if rho is slowly varying. And why is it? How do we measure the slowly varying? Simply in terms of a gradient norm. So we have two terms here on the right side. One is the natural thing. Actually, it's the gradient of the square root of rho squared, which is sort of a natural object. It has sort of the dimension of an energy. But there's another term actually, which is probably not all universal, and it's just sort of based on the rough estimates we do. There's a fourth power of this object. And then there's something ridiculous actually, because there is an epsilon to a power 15. And of course that 15 shouldn't be taken sort of literally. It just shows you that in some sense there was a lot of hard analysis, and it shows you that this is a very long paper. Okay, so any case, that's what we prove. What is epsilon? Actually, epsilon is arbitrary. But the price you pay, so to say, for choosing epsilon too large is the first term here. So there is a term which is not small, right? It's actually, we can estimate, it's something truly local. We can estimate it by integral rho plus integral rho squared. This is not small, but the epsilon in front here is arbitrary, right? So we can choose the epsilon arbitrarily small, but then of course the last two terms become big, but the last two terms are small already anyway, right? If the gradient of rho is small. So you could, of course, for any given rho now optimize over epsilon. We didn't explicitly do it also because of these ridiculous powers appearing, but you can sort of see, right, at the right-hand side, indeed, it's small if rho is slowly varying. Okay, and this is true for all rho, and in that sense, it's a justification of this local density approximation. Okay, maybe I don't say much about this first remark. I mean, as I said already, this last term here, this is sort of, so there's some arbitrariness actually. We can do the estimates differently and get different powers, but maybe this is not really important. I should explain, however, that what we really prove is not quite what we wanted to prove, namely this for the fundamental Levy-Lieb functional, but rather what this F tilde is, it's sort of a grand canonical version of it, or you can also think of it as a suitable convex hull of the actual Levy-Lieb functional. It turns out that the Levy-Lieb functional is not convex, interestingly. In fact, that's one thing that Elliott proved in his fundamental paper in 83. But you can look at the convex hull, and this at least sort of convex hull, where we're thinking about it, actually what it is simply is that if you minimize the energy given the density, you should minimize over all mixed states and also allow for different particle number mixtures. So that's what I mean by grand canonical. So right, the Levy-Lieb functional is determined by minimizing the energy given the density. But if instead of just minimizing over n particle wave functions, you can minimize over all, so to say, grand canonical states having that density. And that's what I mean by the grand canonical version. So it's a functional that's a priori smaller, right, because we minimize over a larger set. And you can think of it as the convex hull of the original functional. Of course, that should not make a difference at all in the slowly varying case. And we certainly expect this theorem to be true for the actual Levy-Lieb functional, but so far we do not know how to prove this. It's simply much easier in practice to work with in the grand canonical setting, okay, which allows us to use sort of more well, typical tools from sort of quantum statistical mechanics more easily. Here's another formulation of the result in terms of if you want some kind of semi-classical expansion, if you want. So another way to think of a slowly varying density is, say, you fix some function sigma, say sigma has integral 1, nice positive function, and then you just rescale it by n to the 1/3. Right? So this density now has an integral that's n, right? Obviously, just by change of variables. And now you can look at this sequence for larger and larger n, right? And what our theorem basically says, or in this case, is you can think of this expanding this in n. So look at the Levy-Lieb functional at such a rho, expand it in n, then the leading term is just the Coulomb energy of the charge distribution rho, right? Which scales like n to the 5/3. The order n term, so sort of if you want the thermodynamic term, that's given by the local expression. It's just the integral of this function f of sigma. And the error term is lower order in n. That's sort of what our theorem says. And if you do the optimization over this epsilon, actually the error term we get is n to the 11 over 12, which is not terribly good, of course, but the point is we get some power less than 1. The true power is probably much smaller than this 11 over 12, but this is so far what we could prove. All right, so now let me actually still, I still have to explain to you what this function f is, right? So again, what the local density approximation says is that up to the Coulomb term, the fundamental Levy-Lieb functional is just an integral of a certain function of rho integrated over x. And what is this function of rho? Well, it should somehow be the energy of a homogeneous system, right? Which you can actually just define exactly this way. So imagine we test, right, the Levy-Lieb functional at some density which is basically a constant over some large set. So this stands for the indicator function, right? So the characteristic function of a set which I write as L times omega. So think of some nice set omega, say a ball or a cube, and then you rescale it by some large parameter L, okay? And you put a density of particles rho 0 there. And now that alone doesn't quite work, right? Because we need a function that whose square root is in H1, right? So it has to, we cannot be too discontinuous, so we have to smoothen it out a little. That's what the chi is doing. So this is a convolution with chi here. So also chi is some nice function, say some bump function, right, of integral 1, compact support. It's basically smoothing things out. So we have a density that's basically constant over a very large region, and then at the end, there's a little smoothing going on, right? And now what we do is we look at this, and now we'll let the system size go to infinity, right? So we look at this energy per unit volume. We have to, of course, subtract the sort of trivial term, the Coulomb energy of this charge distribution here explicitly written out. So once we subtract that, this difference actually has a limit, has a thermodynamic limit, which only depends on this number rho 0 I put here, okay? And that defines the function f. Okay, this is sort of the existence of the thermodynamic limit, which we also proved, right? So here it's written as a theorem. This limit exists, and actually it's independent of the input, right? Of what omega you started out with, and what kind of chi you used for the cutoff. It doesn't matter. It always gives the same function f, right? So this is the definition of this function f that appeared as sort of the local energy in the previous theorem. And this is in some sense standard existence of thermodynamic limit, but it's actually a bit tricky here to prove because of the fact that the density is fixed, right? So this is not sort of quite the usual statistical mechanics where you fix the number of particles, right, in a volume, and you let the volume go to infinity or something. Here we actually fix the density, so it's actually a bit tricky to even establish the existence of this limit. So we had to work quite a bit to do it. All right, so that's the function f. Now, how does it look like? I mean, we don't know what it is, right? We can't compute it. It's defined this way. I mean, we can sketch, we know it's asymptotic, so to say. Here's a sketch of what we expect this to look like. It will be negative for small rho. In fact, it has an asymptotic, which is rho to the 4/3 with a minus here for small rho. Then it will reach a minimum, and then for large rho, it actually increases. It increases like rho to the 5/3. Okay, so these asymptotics are known and sort of also not that difficult to understand. In fact, this rho to the 5/3, you see at high density, basically the Fermi pressure is the most dominant term. So the kinetic energy is the dominant term, and the rho to the 5/3 is simply the ground state energy of a free Fermi gas. Right, so in particular, the constant in front here is just the Thomas Fermi constant, right, which is explicitly written out here. There's also a rho to the 4/3 correction, which is known rigorously. This is simply the Dirac correction. So this is basically, if you think of an ideal Fermi gas, and now you take the Coulomb interaction into account simply by perturbation theory, you just do first order perturbation theory, then you find the next order correction term, which I think actually Dirac computed. So that's why it's called the Dirac constant, which is written here. That's the next order term. And the fact that these two are actually the asymptotics of this function f, this follows from a work by Graf and Solovey. Sorry, I forgot the year. Maybe okay. Philip can tell us later if he remembers. So this is the asymptotics here. In fact, there's also a big conjecture, very interesting conjecture about what the next term here is in an expansion in large rho. This goes back to works in the 50s, in particular by Bohm-Pines and the Gell-Mann-Bruckner, and they reached sort of a conclusion that the next term, I mean, there's a rho log rho term, and then there's a rho term. They are sort of predicted, but so far we're very far from actually understanding this. So this is a big open problem. There has actually recently been some progress in some related but simpler problem, but this is sort of largely open. In any case, this is sort of more remarks here. Actually, I want to focus now on the other end, on the low density case, right? So the low density case here, there's the asymptotics, as I said, it's rho to the 4/3 times a constant, which is here called CSCE for strongly correlated electrons, simply because the low density limit, that's sort of the classical limit, that the Coulomb interaction takes over. That's the dominating term. The kinetic energy is the perturbation. So it's really, you really expect to have a very strongly correlated system. And in fact, the asymptotics is given exactly by just looking at the classical problem, right? So forget the kinetic energy, just classical electrons. That will give you the asymptotic behavior. In fact, if you just looked at the classical problem, the energy is always equal to a constant times rho to the 4/3 just by scaling, because everything scales like an inverse length in the classical case. And that constant is exactly the asymptotic constant here, not surprisingly. It's actually not completely straightforward to prove this, because if you think of what you need to do, right, you have the classical configuration and now you have to perturb by the kinetic energy, but it's a very singular perturbation. So to show that it actually really doesn't have an effect is not completely trivial, but it can be done. So this is the classical asymptotic, the classical constant here. We actually know a lot about this constant. We know it sort of to high accuracy. It's between 1.44 and 1.45. And I will actually explain where these numbers come from. The curve here is a sketch, obviously, right? And it looks here very smooth, but actually we do not expect it to be completely smooth, because we expect this system to have a phase transition, right? So there should be at least a phase transition between a solid and the fluid. Sort of there's the crystallization going on at small density, but there should be a fluid at high density. If one also takes the spin into account, which is really there, one also expects some magnetic phase transition. So there's probably more than one phase transition and probably more than one point of non-smoothness in this function f. Okay, so now for the rest of my talk, I actually want to focus sort of on this, find the cursor here, on this end here, namely on the purely classical problem. Okay, so we can actually just think of the Levy-Lieb functional in this case, right? What we have to do is we minimize the energy given the density. Now we're just minimizing the Coulomb energy. There's no kinetic energy. And then, of course, it's a bit unnatural to think about wave functions, right? Because, I mean, it's purely classical problem. So equivalently, you can think of minimizing over probability distributions, right? So you have a probability distribution over n, over the n electrons, right, x1 to xn, and its one particle density should be equal to rho, right? So for the probabilities, this one particle density is just the sum of all the one particle marginals of this n particle probability distribution. That's the rho. So we fix a rho and we minimize the Coulomb energy, right, over all possible distributions of the n particles, such that the one particle this density is equal to this rho. So this is exactly the Levy-Lieb functional, but now restricted to the classical case. Okay, and as before, there's sort of a trivial term we expect this functional to contain, which is simply the Coulomb energy of the charge distribution rho, which is sometimes called the direct term or the uncorrelated Coulomb energy, just the integral of rho of x rho y over x minus y, right? So the self-energy of the charge distribution rho. So let's subtract that and call the resulting functional, say, I of rho. I guess I stands for the indirect part of the Coulomb energy. If we want to think of the uniform system again, right? So then what we would do is we would look at this functional at a density that's basically a constant. So let's take it to be, say, the characteristic function of some set omega. Let's make this set very big. So if we divide by the volume of the set, then this object will have a limit, right? And this limit is just a constant, which I call here now E U E G for the uniform electron gas. Right? And you see, I chose the density to be 1 here, but the value of the density is completely irrelevant by scaling, right? If I had chosen any other constant rho 0 here in front, it was just scale out as a rho 0 to the 4/3, right? That's what I mentioned before. In the classical case, the energy is exactly proportional to rho to the 4/3, so we might as well set rho equals 1. And at least for this uniform case, right, all we're interested is basically this constant. Okay, so that's the constant that appeared as the asymptotics for small density in this function f on my previous slide. Now, what is it? If you go to the literature, they actually tell you what it is. It's here. It's minus 1.4442. And where does this come from? This is, if you take the Epstein zeta function for the BCC lattice and you evaluate it at the Coulomb point 1, that's the number you get. Okay, so here's the definition, right? So the Epstein zeta function for any lattice. So think of L as a lattice that contains the origin as one of the points. And you sum simply 1 over the distance to this origin to the power s over all points in the lattice, of course, excluding the origin. Okay, so this defines the Epstein zeta function, and this is defined as soon as s is bigger than the dimension of the space, which is now 3 for us always, right? So as long as s is bigger than 3, this is well defined. But just like for the Riemann zeta function, which is sort of the special case in one dimension where you look at the integer lattice, this thing is actually an analytic function in sort of whenever the real part of s is bigger than 3, and you can analytically continue it. It has just a simple pole at s equals 3, and everywhere else it has this holomorphic extension. In particular, it makes sense to analytically continue it to the point equals 1, right? And then I don't actually know how to evaluate this numerically, but in any case, this number you can compute to arbitrary accuracy and it comes out to be 1.44. Okay, here's a sketch of what the BCC lattice supposedly looks like. So now where does this prediction come from, right? Why should it be related to that? Obviously, there should be a lattice, right? We expect the electrons to sort of be on a lattice. It's called the Wigner lattice or the Wigner crystal. We set out to have a homogeneous system, right? So this is not a priori quite compatible, right, with a lattice. But this number, the way you compute it or the way it comes out is basically you look actually at a slightly different system, which is known as Gellium, where you don't prescribe the electron density to be fixed, but you sort of indirectly do by putting in the corresponding sort of neutralizing background charge. So what you do for the classical Gellium problem, right, you have n electrons, they're at positions x1 to xn, and you minimize the Coulomb energy between them. But in order to, make sure that they don't just escape to infinity, what you do is you put in a neutralizing background charge. So you see there's a minus now, there's an integral over some set omega, that's the background. So think of it as a cube or a ball of size n. Okay, and you see the electrons now are attracted by this background charge. So there's a uniform homogeneous background charge. And of course, that background charge has an energy which is here, right? It's the Coulomb energy of the background charge. So now we have a system of n electrons and a neutralizing background charge, and the corresponding energy is given here. And we can try to minimize it over all x. In fact, the claim is that for a large system, this minimum will exactly be by putting the particles on a BCC lattice. That's a big open problem. But if we just assume that, so in other words, let's put them on a BCC lattice and let's compute this energy here in the thermodynamic limit, we get exactly this number. Okay, it's actually a nice exercise to do it. You see how the analytic continuation somehow comes in. It's kind of cute. But in any case, that's what you can do. So that's the prediction. That's where it comes from. Now, why should that be equal to our energy of the uniform electron gas, right? Where we do not allow the particles to be in a lattice because we actually force the density distribution to be homogeneous. And a simple-minded answer would be, well, you can always make it homogeneous by moving the lattice a little, right? So if you imagine that the electrons are on a lattice, this is here the blue points here in the picture, right? Imagine they are on some lattice. And now you just move the whole lattice together, right? Completely coherently over some unit cell. That this is sort of, then you get this red shaded area here. And now you have a homogeneous system by construction. The one particle density will be a constant on this red area. And now you could imagine, well, maybe that's sort of the state of the uniform electron gas. It's really a lattice and you wiggle it a little to get a constant density. So I think this is actually what many people had in mind. But in fact, it turns out that doesn't work. That's too naive. And you can sort of see it from this picture, because if you do this wiggling around effectively, so if you think of this red thing maybe as the background charge, that's effectively what it is, and the blue thing are the electrons, then you see there's an effect, a net charge on the left and on the right boundary here, because there's sort of too much blue on the right and too much red on the left. If you compute the Coulomb energy between this sort of boundary charge, right, then you see the boundary charge is proportional to the boundary area. So you get an area squared. And the Coulomb law is 1 over distance, so you get an area squared over distance, so it's exactly a volume. So it turns out that this gives you a volume shift in the energy. It doesn't give you the same energy at all as you wanted. In fact, you can compute it and you find what you wanted to have, but you get really an order 1 correction, which is just the integral of x squared over the unit cell of the lattice. So based on that, you might doubt, is it really true that this uniform electron gas energy is the same as gallium, right? It could be bigger because this is what this picture suggests. So this is what this trial state suggests. If you take the gallium, you take the lattice and you wiggle it, you use this as a trial state for the uniform electron gas problem, you don't get the same answer. Yet you do if you do things a bit more clever, and this is something we actually did. We can actually prove the two things are the same, indeed. But the simple-minded trial state that I just explained doesn't work. It almost does, but one way you can do it is the following. You still do what I said before. You take your lattice here and you wiggle it around, but you don't keep the strict lattice until the very end. So you think that you have the solid, but actually you immerse the solid in a thin order 1 layer of fluid. That's what this picture is supposed to suggest. I mean, think of ice, and then you have a little layer of fluid around. And as you move the ice, right, to wiggle to get the homogeneous density, the fluid always moves out of the way, right? So the box is fixed, and if you move the ice, the fluid sort of moves around, right? And this way you avoid any kind of building up charge at the boundary as you move, so to say, the block of ice here. Okay, so that's the picture, and that it turns out it works. So in other words, if you want to get a homogeneous system, you can still use the lattice, but you have to melt it a little bit at the boundary of your domain when you do the averaging in order to avoid this buildup of the boundary charge. And if you do that, you can actually prove what is written as a theorem here, that indeed this uniform electron gas energy and the gallium energy are the same. Of course, we still don't know that the gallium energy is equal to this BCC energy, right? That's sort of the problem of crystallization, which is a big open problem, which is only solved in some very special dimensions. But this is certainly believed to be the case. Okay. All right. So I think, yeah, my time is almost, probably it's actually up, but I think I started a little bit late. So let me, I have just one more slide, which is yet another important contribution of Elliott, and very much related to this. It's called the Lieb-Oxford constant. And I want to just briefly explain actually the consequences of this work I just described on this Lieb-Oxford inequality. So what is the Lieb-Oxford inequality? It refers to this classical indirect energy, right? This is, if you want, that's the sort of Levi-Lieb functional in the classical case, where the direct Coulomb energy has already been subtracted. So that's the indirect part of the Coulomb energy, which right? We just argued by scaling simply in the homogeneous case, it's just the constant times rho to the 4/3. Now, what Elliott proved in 79 is that actually for any rho, no matter how wild, right, doesn't have to be nearly homogeneous at all, for any rho, so to say, there's the local density approximation holds as a lower bound for a certain constant, which we call the Lieb-Oxford constant. So I of rho is actually bounded from below by minus some constant times integral rho 4/3 for any rho. Okay, the reason it's known as the Lieb-Oxford inequality is because a year later, Elliott had a joint paper with Oxford where they actually got a much better bound on this constant. I think in the original paper it was 8 point something, and then they got it down to 1.68. And this value of the constant is actually of practical importance. It's not just sort of an academic exercise, because people in sort of practical applications use this inequality to somehow constrain their density functionals, right? In practice, the art, if you want, or I mean, it's an art and the science, of course, to come up with good approximate fundamental density functionals. And one can use sort of rigorous constraints like this one to limit the kind of functionals or the kind of parameters that enter these functionals. So in that sense, actually, the value, the best value of this constant is very important, and it was sort of very important to get it down to some very realistic value like 1.68. Why do I say it's realistic? Well, because now if we look back to the previous theorem I just explained, we can argue that the Lieb-Oxford constant must be at least as big as this 1.44. Why is that? Well, because the Lieb-Oxford constant is certainly bigger than what we would get for the homogeneous system, right? Because this is valid for all rho, and for homogeneous rho, we just get this U, this EUEG, in fact, with a minus, right, in my convention. So the previous theorem says that this EUEG is actually nothing but the Gellium energy. So we have this lower bound, but the Gellium energy is certainly, we don't know that it's equal to the BCC energy, but it's certainly smaller than that, right? Because we can always use this as a variation upper bound. So we get this lower bound. So this theorem actually tells us, gives us a lower bound to the best Lieb-Oxford constant, which is 1.44. So you see there's actually not so much gap in between. In fact, very recently, I mean, the last year or so, we have started to work on trying to improve or trying to make this gap in these upper and lower bounds even smaller. This is sort of work in progress, and maybe the last word is not yet spoken, but we've sort of improved the Lieb-Oxford method with, I guess, if you want computer-assisted proof. I mean, there's some numerical optimization at the end going on, which we're still working on, but it looks like this way we can actually get the upper bound, the Lieb-Oxford constant, down to 1.58, which would mean that there's now only roughly, say, 10% difference between upper and lower bounds. So this is very much work in progress, but I think I thought it's still sort of suitable here. It fits the topic, and it shows you that this is still sort of a very, very active area. So with this, I close, and let me just maybe go back to my initial slide of congratulating Elliott.
Thank you very much, Robert, for this very beautiful talk. We have time for 1 or 2 questions.
Great talk.
Anton, please. Oh, can you wait, please, for the microphone?
Could you go to the slide where you have this very interesting estimate? Yeah, the one for FLL. Previous one. Yeah.
Here, yeah.
Yeah, the theorem. And so on the right-hand side, you have all those gradient terms. But is it known how instead maybe you can continue the approximation with gradient terms? So put some more terms on the left-hand side. So FLL minus the Coulomb term and the local term, and then the gradient term, and then this would eventually modify maybe make the right-hand side a bit less tricky.
Yeah. So I think the answer is, strictly speaking, no, in the sense that we do not know what the next order term is. I mean, there will be gradient corrections, right? So I think what you could do is you could ask the same question only for the classical problem or only for the kinetic energy. And I think there it may actually be true that there are predictions for the next terms. But if you take the sum of the two, they will not be the sum of the next terms, right? So I think in general, it's not known what the next term in an expansion should be. But you're right that one could, of course, in principle, try to, get a next order term and then have an even smaller error on the right hand side.
But in principle, you would expect such next corrections, universal next corrections exist, but they're just not known for a moment.
Actually, I do not. I do not know.
Okay.
I do not know. I'm not sure I would expect it even. I do not know.
Thank you.
Well, let me ask a question. So in practical applications of density functional theory, at least in a condensed state, they usually do it with periodic boundary conditions. So are these developments that you showed here applicable to that case as well?
I would guess, yes, we did not think about that, but I don't, since at the end it's all boiling down to getting things local, so to say, I don't think boundary conditions should matter. So if we put the whole thing on the torus, my guess is that will not change anything, but I haven't really thought about it. But just thinking of the basic structure of the method, I don't think boundary conditions play any role.
So, in the interest of time, I think we need to move on. So let's thank Robert again for a beautiful talk. Thank you.
Thank you.
So the next speaker is Philip Solovey. Are you here, Philip?
Yeah, I am. Can you hear me?
Introduce Philip. Philip Solovey got his PhD at Princeton University, then spent time at the University of Michigan, at the University of Toronto, before moving back to his native Denmark. He's a professor at the University of Copenhagen and the director of the Willem Center of Excellence for the Mathematics of Quantum Theory. Also, Philip is a longtime collaborator of Elliot Lieb, and today he will talk about the Well entropy. Please, Philip.
Thanks a lot. So it's a great pleasure to, well, be with you, even online, and to celebrate Elliot's ESI medal. And I will talk about work I did with Elliot quite some time ago, actually, work that has to do with Vienna also, in the sense that it came out of a conjecture on entropy made by Wehr. So let me just briefly tell you what I will explain to you. So Wehr had suggested back in 1979 that there would be a way to quantify the classical entropy of a quantum state based on the coherent state transform. And he made a conjecture that the states that would have the smallest classical entropy in his sense would be the same states that minimize the Heisenberg uncertainty inequality. And so these are the Gaussian or Glauber coherent states. And Lieb almost immediately proved this conjecture. In fact, you can see here that Wehr's conjecture appeared in 79 and Lieb's proof appeared in 78. But that was just had something to do with how fast things were published at the time. But in the paper from 1978, Elliot also made a conjecture that the same things should hold also for SU2 block coherent states. So not only for coherent states when we quantize one-dimensional or plane systems, but also when we quantize the sphere. And actually, Elliot and I settled this problem in 2012. And actually, the paper appeared in 2014, but I wanted to mention the year 2012 because, in fact, we settled this problem at a conference for Elliot's 80th birthday. Elliot had invited me to join him a few days before, and we were having some great days. And then we solved this conjecture. And actually, Robert in his talk asked that whether I could remember when Graf and I had done the work on gallium, the expansion of gallium. And then I just thought that Yes, we actually did this in 1992, or rather the paper was published in 1992 in a volume celebrating Elliott's 60th birthday. So in any case, let me go back. So Elliot and I solved it in 2012 for SU2, and then a few years later, we generalized it to SUN for general N, but not in the most general setting, and I'll try to explain it. The way we solved the conjecture was to cast it in sort of a greater context of quantum communication channels. So we actually proved an inequality on minimal output entropy for particular quantum channels called the universal quantum cloning machines. I mean, you cannot clone, we know that in quantum theory, but you can still ask for the quantum channels that are the best cloners sort of uniformly in the input state. And what we did, we determined the minimal output entropy of these channels and actually showed that that implies the estimate on the Val entropy that had been conjectured for Elliott, for SU2, and also for SUN. So this was the abstract of the talk, and let me then just briefly go through what I will tell you. So I'll explain coherent states and quantizations. I will explain the states of minimal classical entropy, the classical entropy defined by Val. Then I'll go to the SUN case and explain the coherent states for SUN and the classical SUN entropy. And I will then explain what it has to do with these quantum communication channels and show how to, or at least briefly explain how to prove the minimal output entropy of these quantum communication channels and why they actually then prove the classical SUN entropy. And this will be done by reformulating the problem in terms of majorization and then using a bosonic second quantization language. And I'll hope I'll get to at least briefly explain how that proof goes. So let me start with quantization. This is probably well known to most of you. This is the classical case where I have the classical phase space R2n, so the position and momentum of a particle moving in n dimensions. And we all know that the quantum description of that is to look at L2 of Rn. And by quantization, we mean whenever we have a function on the classical phase space, an observable, a real function on the classical phase space, we would like to get a self-adjoint operator on the quantum space. Now, if we have such a quantization map, I mean, something that goes from functions to functions on the phase space to operators, then we can sort of dualize it and get a distribution on the phase space just by this formula down here. So imagine that I have a quantum state psi. So here by quantum state, let me just emphasize, I'm talking about a pure state. We could also think about a mixed state where we would have, I put it down in the footnote here, we could in general think of density matrices. But for most of what I will be talking about, it will only be important to look at the pure state. I mean, the mixed states have entropy even at the quantum level. The pure states have no entropy at the quantum level, but they do have entropy when we see them classically. So the Val entropy for a pure state will be non-zero. In any case, I can do the expectation value of my operator A in my state psi and hope that this is somehow a distribution, or it will be some type of distribution over phase space integrated against this function that I had quantized. The only problem is that depending on what quantization you are using, you may not get a positive function. I mean, if you use the famous Weil quantization, then the phi you get will be the Wigner distribution of your psi, and that will in general not be a positive function. You cannot think of it as a probability distribution. And for that reason, Weil suggested that it was better to use the coherent state quantization or the Wick quantization that I will explain now on the next slide. So coherent states, so these are the states that minimize the Heisenberg uncertainty principle. So these are Gaussian functions and shifted so that they are centered classically centered around the point Q and P, right? So their expectations in position and momentum would be Q and P. Or we can also think of them that if we do that, they are like eigenfunctions of the operator x plus nabla, I mean the quantum operator x plus IP, and they give the eigenvalue Q plus IP. So these are normalized states. These are these normalized Glauber coherent states. And I can then define a quantization map when I have these. So I think of these states as the states that sort of classically best represent the point QP. So I look at the projection onto these states. And if I have a classical function on phase space AQP and I want to create an operator, I simply take my function AQP and integrate it against this projection. So this is a operator valued integral. I do this integration and I'm getting some operator on the classical phase space. And in fact, if you take the operator 1, you will get the operator 1 coming out with the normalizations that I have chosen here. And if I then turn this around, as I said before, to get a distribution, I can get what Elliott called the lower symbol. I think Berezin called it the covariant symbol. Some people call it the Fushimi Q function. And it is exactly the state psi, so my quantum state, in a product with a coherent state, and then squared. And this object obviously is positive, I mean, not negative. It will be between 0 and 1, and it will be a probability distribution against the classical measure, the QDP, divided by 2 pi n. So I have a classical probability distribution, and it makes sense to talk about its differential entropy, if you want. So the classical entropy, as defined by Werl, is simply the entropy of this distribution with the entropy function distribution log distribution minus T log T. So this is a positive quantity that in some sense will measure the entropy of this quantum, the quantum state. And the conjecture that Werl made was that the classical entropy of any state psi is bigger than or equal to the classical entropy of one of these coherent states. So the coherent states simply minimize the classical entropy. And as I mentioned in my very first slide, Elliott proved this almost immediately. And by noticing, so the proof was based on the Young and Hausdorff-Young inequalities. If I just go back and look at the definition, you can see that this object here is integrating against a shifted Gaussian and an e to the IPX. So it involves a convolution and a Fourier transform. So it's natural that you can rewrite it in terms of Young and Hausdorff-Young. And remember, what we're trying to prove is that that the minimizer is a Gaussian state. And what Elliott noticed was that, well, Young and Hausdorff-Young, the sharp Young and Hausdorff-Young inequalities are exactly optimized by Gaussians. So in fact, when you rewrite things in terms of convolutions and Fourier transform, you will get this inequality when you use the sharp inequalities. One should say that the Young and Hausdorff-Young inequalities are not for the entropy function, but for powers. But then the idea is that you rewrite the entropy, the function minus T log T, you rewrite as a derivative in the exponent of the power T to the P, and you use the sharp inequalities for the T to the P. Carlin, quite some time later, proved the uniqueness of the minimizer. So Elliott had proved this inequality, but not that that you get equality only when psi is the coherent state. But that's exactly what Carlin then proved. Now, when we then studied the SU2, a byproduct of what we did was that we actually could improve this inequality, because we could prove that this inequality holds not only for T log T. Our method that goes through these quantum communication channels actually allowed us in our paper back in 2014 to show that the inequality holds for any concave function f, not just T minus T log T. Okay, and I'll get to where that comes from, this fact that it can be done for any concave function. Let me come now to the SUN coherent states. So I've discussed the coherent states for the classical phase space. I mean the classical phase space. If you want the particles moving on Rn. Now I want to go to the case where you've quantized a group or the action of a group on a symmetric space. And let me start by actually giving you the Hilbert space and then come to the classical space afterwards. So SUN acts irreducibly on a space where I take, so SUN acts on Cn, naturally, that's where it's born. I can now take the symmetric tensor product of Cn with itself m times. Now that space is, SUN will act on that space by simply acting on each of the factors. And that will be an irreducible representation of SUN. And in fact, if n is equal to 2 in the case of SU2, it will give us all the irreducible representations. In that case, the representation HM would correspond to the spin m over 2. So m is here an integer, and if we were doing the representation of SU2, it would be the case where the spin is m hat. And these are, of course, all the irreducible representations of SU2. Now, for SUN, it's not all the irreducible representations. If you think of Young diagrams, these are the irreducible representations that correspond to one row Young diagrams. And we can prove the conjecture about coherent states minimizing the Weyl entropy only for those representations. So it's actually still open for other representations of SUN when n is bigger than 2. But let me tell you what the coherent states are for the on this space here, and then I'll come to what is actually a quantization of. So on this space here, it's actually very, very simple to explain what the coherent states are. They are simply the pure tensor products of one state U in Sn with itself. I mean, and the m-fold tensor product of U with itself is clearly a symmetric tensor product. If you think in terms of bosons, that this space is the space of m bosons with n degrees of freedom. So if I have m bosons with n degrees of freedom, then you can think of this as the condensate states, the state where all m particles are in the same state. And these are then what corresponds to our coherent states. These are states in here, and these are our coherent states, and they are actually indexed. So the state, as I said before, the state is really the projection, meaning that the phase of U does not appear. So the state is actually represented not by a unit vector in Cn, but rather a unit vector in Cn modulo an overall phase, which is exactly what we call the projective space Cpn minus 1. And Cpn minus 1 is indeed a classical phase space. And what I can think of is I started with a quantum space, but in fact, I can think of this classical phase space, and that what I'm doing is I'm quantizing this classical phase space, and I'm quantizing using these coherent states. So if I think of it in that way, so Cpn minus 1 is a classical phase space, Hm, the symmetric tensor, m-fold tensor product of Cn with itself, is the quantum space, and the quantization map. So I take a function A defined on projective space, and I integrate it against these coherent state projections, the things that project onto condensates. And I do an integral over Cpn minus 1. Cpn minus 1 has a natural, if you want, it's the Liouville measure. On this classical phase space, I'm normalizing it to be a probability measure. And if I normalize this du to be a probability measure, then if I multiply here by the dimension of Hm, then my quantization map is normalized in such a way that the function 1 goes to the identity. Now, this may all seem very abstract, But in fact, in the case n equal to 2, we understand it much better than Cpn minus 1. I mean, Cp1 is actually S2. It's the 2-sphere, and it's what is often called the block sphere. It's the representation of all unit vectors in 2 dimensions when you do it modulo a phase. So, that was the original case that Elliott had conjectured back in his 78 paper, that the Weyl entropy should hold in this case when S2, when we were looking at the phase space S2. Let me anyway stay in the case of the Cpn minus 1, and the Hushimi function is then whenever I have a state rho on my quantum space, the Hushimi function becomes a probability distribution on the classical phase space on Cpn minus 1, and it's simply the expectation value of the quantum state rho against this tensor product mu. So this is a probability measure, and I can again talk about its entropy. So the classical entropy inequality says that, well, whatever representation I'm looking at of these particular types of representations of SUN, and any concave function I have, because I can prove it for any concave function, it's not only the entropy function, but in particular also the entropy function. But for any concave function and all stage rho, so here I did not even say that the state had to be pure, but it's quite clear that you will always do best by looking at a pure state. But for all states on the representation space, the integral of a concave function of the Hushimi function is bigger than or equal to if I insert the coherent state itself. So remember these states here, the pure tensor products, they were coherent states. And I'm saying that the minimal entropy will occur for a coherent state. And that solved the more general case of Elliott's conjecture from 1978. And it does it for all representations of SUN of the form that correspond to one row Young diagrams. So we actually proved this result in the 2014 paper in ACTA in the case n equal to 2. But then we realized a few years later that we could generalize it to SUN. And actually the proof for SUN is in some sense simpler than the proof we originally had for SU2. Now for n equal to 2, as I said, we're talking about the block sphere, and the entropy function was exactly what Elliott had conjectured in 1978. I should maybe mention that in this case, for SU2, for Elliott's conjecture, there had been lots of works trying to prove the Elliott's conjecture, Elliott's generalization of Weyl's conjecture. And Schupp, who I saw was in the online audience, actually had done great progress on proving it for many cases of spins before we actually settled the full thing in 2014. Let me just mention that if you go to SUN, when n is bigger than 2, then these classical phase spaces are somewhat complicated. These projective spaces, they are not spheres. I mean, unless n is 2, as soon as n is bigger than 2, these are actually not spheres. The spheres would not be classical phase spaces. So now let me come to the generalization to quantum channels. So as I said, the idea in our proof was to generalize the problem from the situation of finding a classical entropy to actually relate it to quantum communication channels. And how does that make any sense? I mean, the point is that this phi infinity, this Hushimi function, so phi infinity was the function that from a quantum state gave us this the distribution over classical phase space. So it's a map from a quantum state to a classical probability distribution. So we can think of it as a map in a sense, a map that sends information, transfers quantum information to classical information, right? So it gives us something from a quantum state to a classical probability distribution on phase space. We noticed, actually, Elliot and I had worked on this years ago. We had introduced something we called quantum coherent operators. We didn't realize at the time that they were quantum channels, but we introduced these back in the early 90s. And at that time, we hadn't thought that they could be used at all to prove the conjecture. But that's what we then realized in 2012. And let me explain what these quantum channels are, these quantum cloning machines, universal quantum cloners. They're actually quite simple to understand in the context of SUN. So remember that HM, the quantum space HM that I was looking at, was the m-fold symmetric tensor product of Cn with itself. I had it all the way back there. HM was the m-fold symmetric tensor product of Cn with itself. I would now, instead of going to a classical situation, this I call phi infinity, I want to think of a communication map, something that transfers quantum information from one Hilbert space to another Hilbert space. And I actually want to go from HM, I mean the thing that is the m-fold tensor product, to something which is the m plus k-fold symmetric tensor product. And it's fairly easy to do this. You take your quantum state, which lived on this space, then you simply tensor with the identity on the remaining k. So this is something that live of m-fold tensor product, and then I simply tensor with the identity on the remaining tensor product. That will of course not be symmetric. I need something that acts on the symmetric space, but then I simply just project it down to the symmetric space. So I do the projection here, that's the projection down to the symmetric m plus k-fold tensor product. Now we would like this map to be a trace preserving map, and that requires some constant here. I put this constant in blue. There will be a lot of these positive normalization constants, and they play no role whatsoever for the proof. It's just important that they're positive. So there will be lots of these constants, and you can calculate all of them, but we don't need to, and it would be complicated, some complicated combinatorial factors that come in. So I have a map here that takes a state from HM, the m-fold tensor product, to the m plus k-fold tensor product. And what we wanted to do was to find their minimal output entropy. In exactly the same way as the phi infinity, we were looking for the minimal output entropy and going from a quantum state to a classical phase space. So let me explain how we determine the minimal output entropy of this quantum channels. Maybe let me say one word about how can we think of this as a universal quantum cloner? I mean, you can just think of the rho as if the rho was something that was living on HM. I mean, you simply try to spread it uniformly to make copies of it over in the other tensor product. Okay, so here's the theorem that we prove. It's the theorem that's the generalization of the classical situation. The classical situation studied the map phi infinity to a classical distribution. Now we study a map that go from an HM, go k up, and if you think of SU2, it would go up k over 2 in spin. Any concave function, any state, we prove that the trace of any concave function of the output is greater than or equal to the trace of the same concave function of the output of a coherent state. So the coherent state minimizes the trace of concave functions. Now, why does the classical entropy inequality follow from this? Well, because there is a classical limit. In fact, if you take the object, the thing that's written here for any state, you have to normalize it in the correct way. So you take your concave function, you evaluate it on this quantity here, take the trace, divide by the dimension of the space you go into, and go to infinity, it's not difficult to see that this actually converges to the integral. So if we can prove the inequality for k, it would follow in the limit in the classical case. Let me mention that we are actually able to we're not able to find the minimizer as Carlin did for the Glauber coherent stage, because we're getting it as a limit. So in that sense, the question of uniqueness of the minimum in the classical case is still unknown. Okay, so let me spend a little time explaining how we prove this. We notice that instead of looking at traces of concave functions, which is what we did in this case here. So here we talked about traces of concave functions. There's actually a reformulation of this property that something is controlled, that a trace of a concave function of one operator is greater than the trace of a concave function of another operator. It can be reformulated in terms of what's called majorization. And in fact, this is what's called Karamata's theorem. So we can equivalently prove, instead of considering traces of concave functions, what we want to prove is that for all states, the ordered eigenvalue of the output of the coherent state will majorize the ordered eigenvalues of the state phi k of rho. That's equivalent to saying that the trace of a concave function of this will be bounded by the trace of a concave function of that, as I said here from below. And what does majorization mean? Well, if I list the eigenvalues, so these are the eigenvalues of my matrix, of a matrix A, or in general, just any sequence. If you have a sequence of J values, it majorizes a sequence of another sequence of J values. If the first one, A1, is bigger than B1, then the sum of the first two are bigger. So A1 plus A2 is bigger than B1 plus B2. A1 plus A2 plus A3 is bigger than or equal to B1 plus B2 plus B3, and so on. That's what I wrote here, that the partial sums dominate, and the final sum is an identity. This is the trace property. These operators have the same trace. These are trace preserving, so the trace of this is the same as the trace of that. So the sum of the eigenvalues, they're really the same. So what we would like to prove is the inequality that the partial sums of this is bounded above by the partial sums of the thing coming from coherent states. And we found it convenient to reformulate the whole problem as bosons. As I said before, we could think of these representations as being M bosons living in having n degrees of freedom. So we can think of rewriting the whole problem in terms of creation and annihilation operators and using second quantization. So here I introduced the creation operator. Right? So it maps the representation space HM to the representation space HM plus 1. It adds an additional boson. I wrote the definition here. You think of a basis. So here I was writing everything in terms of a basis of Cn. So the AI is, the I here is indexing an orthonormal basis of Cn. I add bosons in the state EI corresponding to that basis by tensoring, doing the tensor product. So I go from HM to HM tensor Cn, and then I symmetrize, and then you put in the correct normalization. So the map, the phi k map that I had written earlier in the form, let me go back, in the form there, saying that you could think of the quantization map or the communication map, this quantum channel, tensoring in by the identity and then symmetrizing. Well, you can write it conveniently in terms of creation and annihilation operators. So this is actually the Krauss form of the quantum channel. These are the Krauss operators that we have on both sides. You you get a map acting on M plus K bosons by killing K bosons, acting with the thing that acts on M bosons, and then recreating the K bosons again, and then you're summing over all indices that run over the basis. And again, there's a normalization constant here that does not really play a role. And then I can actually now give you the proof that the eigenvalues of this object will be majorized by the eigenvalues of the coherent state, meaning I put in a coherent state there. So the first thing, I guess I mentioned it already, ordered eigenvalue sums are convex. That means that I can certainly think of the rho here as a pure state. It's easy to see that the best you want to do is to plug in a pure state. And the next thing is that if I have a pure state, so now I've plugged in this psi here, so pure state, then there is, well, I guess it's sometimes referred to as supersymmetry. I mean, the fact that the eigenvalues of an operator A star A is the same as the eigenvalues of the operator AA star, except at 0. So A star A and AA star have the same eigenvalues, except at 0. We can actually rephrase this, saying that the eigenvalues of this will actually be equal to the eigenvalues you get by turning this thing around. So if you thought in here I had the psi for the rho, but if I now turn it around and put the psi on the other side, I'm actually getting this matrix indexed by j's and i's. So this is a huge matrix where the i's on this side run over the I from 1 to n, and the j's run from 1 to n. This matrix will have the same eigenvalues except at 0 as this eigenvalue. So it's enough to show that this object here, the eigenvalues will be majorized by the thing I get by putting in a coherent state, a pure product, tensor product here, in which case I can easily calculate this operator. Now this looks a little bit funny because we have the a's to the left and the A stars to the right. So it's natural to say, well, that's normal order. Let's put all the A stars to the other side and the A's to this side. Because then the thing I would get if I had written that, if the A stars were to the left of the A's, expectation value in psi is what we call the reduced density matrix. Ordered and normalized in some way. So I can try to do this. I can try to normal order. And every time I pull something through here, I get a delta function and between I1 and J1. And this is simply telling me there's a way you can, if you think about it for a moment, you can see that as you normal order here, you will get all the different density matrices from 0 and up to K coming in with some extra delta functions on them. But extra delta functions are like identities. So in fact, this is exactly like the quantum channel. So the gamma you can actually rewrite as a sum, again, with some constants that do not play a role, of the reduced density matrix corresponding to K minus L. And then it's exactly the quantum channel phi L that comes in that map me from K minus L and up to K again, so that I can go up to the right dimension. So this formula was actually found by Kiribella. And the coefficients do not really play a role. But now I can prove the majorization result by induction, because I can prove it. I can do induction on K, because here I have a sum from 0 to K. So if I can show that every term in this sum majorizes from 0 and up to K minus 1 by induction, then because the guys that majorize, these guys, are actually all easy to calculate, it's not difficult to see that when you do the sum over them, they will also majorize. And now to get the last term that you don't know, I mean, we do induction on K, and the only thing we don't know here is the last one when L is equal to K. But when L is equal to K, we just have an identity operator here. It's the 0th. We have K minus L equal to 0, so it's just the 1. And in that case, of course, we get the same whether we have the term there or the unknown gamma psi. So in that case, the result is obvious. And then just from this formula, we are able to prove the majorization result, and in this way we can prove that the trace of concave functions are optimal whenever we have coherent states. So this was a very nice collaboration that Elliot and I had. I enjoyed it very much. We've tried to do it for other groups. We are going through all the groups we know one at a time, but we've not been able to prove it for anything else than so far SUN in the symmetric representations, but it's been very enjoyable. I want to thank you all for your attention and congratulate Elliot on receiving the ESI Medal 2021. Thanks a lot.
Philip, for your beautiful talk. So we have time for questions, and there can also be questions from the audience following online. Just raise your hand. Sasha is watching, or write something in the chat. Anton, please.
I always have questions. I don't know, maybe other people want to. Yeah, thank you. And Philip, thank you for a beautiful talk. So as you pointed out, CP(n-1)s, besides n=2, they are not spheres, but they are coadjoint orbits of SUN. And in principle, one can imagine similar problems for other coadjoint orbits, where also the Cn representation of which you were taking symmetric powers would be replaced by some other SUN representation. Of course, I don't know whether this makes a lot of sense for quantum communication or other applications, but did you consider such things, and would your methods work? What would you expect? Thank you.
Yeah, we considered it. We actually tried to look at all the representations of SUN. And as you said, we looked at the corresponding coadjoint orbits. I don't know if our method will work. It did not work so far. Certainly the question can be asked for these quantum communication channels, just essentially by the same type of procedure, using some Clebsch-Gordon types of representations. I mean, if you think of going, I mean, very general, I think people are studying what they call invariant quantum channels, where you could think of doing, think of one Young diagram, and then you tensor it with another Young diagram, and you write that out in a Clebsch-Gordon series. So if you do the tensor product of the two representations, of course, it will not be irreducible, but you could then project onto whatever irreducible component you would like to have. And that would actually define for you a quantum communication channel from one irreducible representation of a group, or here in this case SUN, but in general also other groups, from one irreducible representation to another irreducible representation. And you might ask in general, what is the minimal output entropy? And you could hope that it was something that it would again be given by the corresponding coherent states. I mean, the highest weight vectors for your representations. I think our original thought that this was true. I'm not so sure anymore, but this is an interesting question, and this is sort of the program that Elliot and I have been thinking about for quite a while.
Yeah. Well, then let's thank Jan Philip again.
Beautiful talk.
The next speaker will be Jakob Yngvason, who has a special piece of furniture here for his laudatio. I'm looking forward to that. Jakob is Icelandic. He got his high school degree there, and then went to university at the University of Göttingen, went back to Iceland, but then came back to Vienna, came to Vienna as a professor, as a successor of Walter Thierry. Jakob actually doesn't need any introduction here at the ESI, because he used to be the director of the ESI for many years. Now he is the president of the ESI Association. And I should explain perhaps that the ESI Association is the organization that initially ran the ESI when it was created. Would also like to add that some of the people who were involved at that time, visionary people, and it's because of these people that the ESI exists today. I just mentioned Peter Michor and Klaus Schmidt and Wolfgang Reiter and Heide Narenhofer is here. I think that Harald Grosse is here online. So it's thanks to these people that the ESI actually exists, and also the ESI Association exists, and Jakob is the president of this association. But now his job is to give the laudatio. Could I please ask you to come to the podium? And I'm looking forward to your talk.
So, thank you, Christoph. Okay, so ladies and gentlemen, colleagues and friends, dear Elliot, it is both an honor and a pleasure for me to deliver the laudatio for Elliot Lieb on the present occasion. As Christoph already explained, the recipients of the ESI medal are selected by the International Advisory Board of the Institute. And let me start by reading the citation for this year's prize. This can be read, I think. Professor Lieb is honored for his deep and groundbreaking mathematical analysis of fundamental problems and models of many-body physics, foremost his works of recent years, which continue to be outstanding and inspiring to a new generation of mathematical physicists. Two highlights in the realm of Coulomb systems are a mathematically rigorous justification of the local density approximation in density functional theory, and the proof of the equivalence in the thermodynamic limit of three different definitions of the minimum energy of a homogeneous electron gas, joint work with Matthew Lewin and Robert Seiringer, and we have also heard in the lecture of Robert about this work. Now, Elliot Lieb is indeed eminently qualified for the ESI medal. He has been a towering figure in both mathematical physics and mathematics for the past 60 years, and during this long time span, he has constantly enriched both disciplines by hundreds of seminal papers of highest quality. His output is most impressive just by its sheer quantity, which is rare in mathematical physics. And let me just bring here some numbers. His publication list has about 400 items to date, including 300 original research papers, many review articles, and 4 books. The selecta of his works, published by Springer in 4 thick volumes, amount to 2,800 pages. One volume, titled Stability of Matter, is now in its 4th edition. Since Elliot has always worked on a difficult and important problem, these numbers are truly amazing. Such numerical indicators, however, are less significant than the quality of his work. Characteristic for his style is a combination of formidable mathematical skill with good taste. One of the many things his younger collaborators learned from him is that not every difficult problem is worth working on. The selection of good problems is an essential part of the art of mathematical physics. And Elliot has certainly solved many good problems. His papers also distinguish them by the thoroughness of the arguments, in accord with another rule he imprints on his younger collaborators: write everything in such a way that you can explain it to your grandchildren in due time. Elliot's influence as a scientist is really extraordinary. He has to date had about 100 collaborators and been a mentor to 2 generations of mathematical physicists. He has twice been the president of the International Association in Mathematical Physics, and many members of the executive committee of the IMP, which is elected by the members of the association, have been past or present co-workers of Elliott. This includes Robert Seiringer, who recently finished the latter of his 2 terms as president of the International Association of Mathematical Physics. Now, his role in the foundation and the initial years of this institute here had also been mentioned. And it was, of course, extremely valuable to have Elliott here as a member of the International Advisory Board for many years. Now, let me recall some biographical facts. Elliott was born 1932 in Boston, but at the age of 5, he moved with his parents to the Bronx in New York City. So he sometimes stresses this, that he is really a child of the Bronx. But his university studies were at the, again in Boston or Cambridge, at the Massachusetts Institute of Technology. After his bachelor, he did not continue right away at the, well, as a, I think Rudolf Peierls in his autobiography, he mentions that Vicky Weisskopf thought it would be good for Elliott to go abroad. And so at the initiative of Weisskopf, Elliott went to Birmingham, to the group of Rudolf Peierls. However, Peierls was not his PhD supervisor, well, to the extent that that Elliott needed a supervisor at all. It was Samuel Edwards. But Peierls, of course, noticed that there was something very special about this young man and tells some stories in his autobiography. I will just recount one. When Elliott was in Birmingham, there was a Japanese student coming to the group of Peierls. And in order to help this student to learn properly English, it was thought to be a good idea to put him in the same room as Elliott. Now, after a year, however, it turned out that the English of the Japanese student had not improved very much, but on the other hand, Elliott spoke fluent Japanese. And this affinity for Japan, in fact, continued because he went after his PhD as a Fulbright fellow to the Kyoto University in Japan. And he has been really very much fond of Japan ever since. In fact, in his house in Princeton, there is a Japanese room where I once had the pleasure of attending a tea ceremony celebrated by Elliott. Anyway, then there are here several stations of his further career, and let me just be very quick. He was a research associate with, in particular, at Cornell. One story he told me about his stay in Cornell was that in Cornell he wrote a paper with a Japanese collaborator on the polaron problem, which is one of the themes that has been recurrent in his publications. In fact, over decades, very, very difficult problem, and Robert has also been involved in that. Anyway, so his first paper on the polaron was in 1960, and one of the things they did, he and his collaborators, was to prove a lower bound to the ground state energy. And that was, of course, at this time, something completely unheard of. People didn't prove lower bounds, they proved the upper bounds by variational functions. And at Cornell, he had a discussion with Feynman, who really got very angry that he would have this stupid idea of proving a lower bound, which, however, of course, Feynman was completely wrong on this, but this shows, so to say, how the spirit was at this time. Anyway, so let me proceed here and over several stations, in particular at Yeshiva University, where he met his longtime collaborator and friend, Joel Leibowitz. He came finally to Princeton in 1975 as a professor of mathematics and Higgins professor of physics, so he was professor in 2 departments. And he retired in 2018, but he still has his office in Jadwin Hall, and this, as we have heard, is still very active. Now, he has, of course, received many honors in his long career. And I just listed here some which could fit on one slide. So this is by no means a complete list. But he has been elected member of many learned societies, including the US National Academy of Sciences, the Austrian Academy of Sciences, the Royal Danish Academy of Sciences, the Chilean Academy of Sciences, Academia Europea, and last but not least, the Royal Society of the UK. So he had to sign his name in the book of fellows, where Newton was one of the first people to sign. It's the same book. He holds honorary doctorates from 4 universities, Copenhagen, Lausanne, Munich, and Birmingham. And among his many prestigious prizes, as again, this is not a complete list, I just mentioned the Heinemann Prize of the American Physical Society and American Institute of Physics in Mathematical Physics, the Birkhoff Prize in Applied Mathematics, the Max Planck Medal of the German Physical Society, the Austrian Medal of Honor for Science and Art, das große Ehrenzeichen von Österreich für Wissenschaft und Kunst. Das ist eine sehr große Ehre. Also it's a very high honor because the number of foreign members is strictly limited. And the last I mentioned here is the Henri Poincaré Prize, awarded by the IMP every 3 years. By the way, 2 other recipients of the Henri Poincaré Prize, which is the highest distinction of the IMP, are Robert Seiringer in 2009 and Jan Philip Solovey this year. Now, I come to his research. And here is just a list of his main research areas. Of course, there is no way that I can do any justice to all this. This is just a list. I will say a little bit about one subject a little later. But some of this has already been mentioned, in fact, by Christoph. Models of statistical mechanics is one topic, and especially exactly soluble models. And the celebrated example of this is this computation of the residual entropy of 2-dimensional ice, where he rigorously verified Linus Pauling's back-of-the-envelope calculation. And this is, so to say, one of the high points in statistical mechanics of exactly soluble models. The other anything comparable would be the Onsager solution of the Ising model. Now, many-body quantum physics has, of course, been a very major theme in all his work, including the Bose gas. I will say a little bit more about that, and Bose-Einstein condensation. Then there are entropy inequalities, including strong subadditivity of the von Neumann entropy, which is a basic problem of quantum entropy that was joint work with Mary-Beth Ruskin. In Coulomb systems, the Thomas Fermi theory and density functional theories, and we have heard in the lecture of Robert a lot about that. But that is by no means all the exact results on atoms and molecules, Hartree and Hartree-Fock theory, and all this is described in his selector volume, or selected papers on this subject are in that volume, which is titled Stability of Matter. Well, quite generally, the introductions to these 4 volumes of his selector are very good reading to get an overview of the many important results that he has come up with in his life. Further subject here, matter in strong magnetic fields, harmonic maps and liquid crystals, quantum electrodynamics, the second law of classical thermodynamics, also the third law was mentioned, and then many inequalities in functional analysis related to quantum, usually quantum mechanical problems, bear his name, and here is a list of some of them: Braskamp Lieb inequality, Bresis Lieb inequality, Araki Lieb inequality, Temple Lieb inequality, Lieb-Thirring inequality, Lieb Oxford inequality, Lieb Robinson bound. The Lieb-Thirring inequality was the basis of the proof by Lieb and Thirring of stability of matter, which enormously simplified the first proof of that. So it was given by Dyson and Leonard several years earlier. But as Dyson somewhere wrote, he and Leonard, when they proved stability of matter, it was like going through the jungle with a machete and just carving their way through the woods. Very long and strenuous work, of course, extremely admirable, but the problem was that it didn't give a very good constant, because as Thirring once said, I recall, well, in that paper, they had to make a lot of estimate, and they lost on, and in fact, it was about 40 pages and on every page they lost a factor of 2. So in the end they got a very bad constant. But Lieb and Thirring, they really, to say, flew over this tropical jungle and got a very reasonable constant. And this is even still a research area of improving the constant, generalizing, and so this has also been a very influential work. Okay, but I have to press on. And what I want to do now in the remaining minutes, well, there are not so many, in fact, but let me see how far I can get. I just want to give an example of very recent research. Namely, as I mentioned, beginning, the prize is given for research from the last 10 years. And during this time, in 10 years, Elliott has published about 60 publications. And some of that work was described also in the lectures by Robert and Jan Philip. But here I want just to mention one theme, which is the properties of the interacting Bose gas. And the interacting Bose gas with its subtle quantum mechanical correlations captured Elliott's interest early. His first paper on this topic dates from 1960, and his by now highly cited paper with Werner Liniger on the one-dimensional Bose gas with point interaction was published in 1963. At that time, that paper was rather academic, one can say. That was a model which they could solve exactly, which is quite remarkable. But in the past 10, 20 years, this has become of great interest, and because nowadays people are able to prepare experimentally such one-dimensional chains and study them. So this is, if you look up Lieb-Liniger, this is one of his Lieb-Liniger model, one of his most highly cited papers. This first paper on the Bose gas was, in fact, a little earlier, 1960, on the hardcore Bose gas. And now I'm going to say something about the very recent work, which, however, has its roots in a paper of Elliott from 1963, but where he and his co-workers have recently published beautiful papers with new insight. And here one can say, in general, it is a characteristic of Elliott's mode of working that he has a great stamina in dealing with important and difficult problems, which may take decades to make progress on. And with such problems that he considers rightly important, he may come back to them repeatedly over time spans of decades, during which he has been dealing with entirely different topics, but it appears that he has been working on the old problems subconsciously. It's in a sort of a background mode of his brain until something new has emerged. And the Bose gas is precisely one such theme. Now, more than 30 years after his first papers on the Bose gas, a paper came out in Physical Review Letters with the title "The Ground State Energy of the Low Density Bose gas." It's only four pages, but it this is this paper here. But it solved finally a problem which was a 40-year-old problem, namely to get an asymptotically correct lower bound for the ground state energy. And the best lower bound to that date was found by Freeman Dyson in 1957. But this problem is one of these which had certainly been on Elliott's mind really for 40 years. It was clear that he had really always subconsciously had this in mind. Now this paper turned out to be very influential because it set out a new activity which is still vigorously pursued by many research groups. And the developments until 2005 are described in this monograph, which has 4 authors, which have all been, you have all seen here in person or virtually. And, but this was, so to say, the status as of 2005. The later developments have in fact built on this very much, but they have also gone other paths, namely to make Bogoliubov theory rigorous or to go beyond Bogoliubov theory, which is mainly work in physical terms in momentum space, while these original these papers or the contents of the book are mostly dealing with methods which can be formulated in configuration space. However, this monograph does not include a highly original approach to the problem that Elliott published in 1963. And in the past 2 years, he has come back to this approach with Eric Carlane, Markus Holzmann, and Ian Joslin. And his so-called simplified approach is based on very plausible but still unproved assumptions about the ground state wave function of a Bose gas. But if this assumption is accepted, many important properties can be derived both by rigorous mathematical analysis and numerical computations. So it is a big challenge, of course, to prove this assumption. I will say what it is, but just as a little analogy, or maybe it's a little far-fetched comparison, you know that the Riemann hypothesis is not proved, but there is lots and lots of literature about which results would be true if the Riemann hypothesis were proved. I'm not comparing this assumption, of course, with the Riemann hypothesis, but still there is a certain analogy here. Now, so let me see, I have here something on, yeah, here is this paper from 1963, simplified approach to the imperfect Bose gas. Imperfect means simply with interaction. It does not mean that the gas is somehow has fault or something like that. It just means that there is interaction. Now the setting, and I think I have now to speed up a little bit, but maybe I can say something in 5 minutes. The setting of the set of a homogeneous Bose gas, so we have n particles in a box of volume V, and we consider the thermodynamic limit where the volume tends to infinity and particle number, and keeping the density fixed. And the Hamiltonian is the usual one, as you saw in Robert's lecture, except that here you don't have the Coulomb interaction, you have a short-range repulsive interaction potential. And for dilute gases, the problem is characterized by the scattering length of the interaction potential. I do not have the time to explain what scattering length is, but you can think of, if you think of V as a hardcore potential, then the scattering length would just be the radius of this core. And this scattering length is a more general concept. And dilute means simply that this scattering length is small compared to the mean particle distance. So they have a small parameter here in the problem. And we denote the ground state wave function by psi 0. And now the starting point of the simplified approach is the observation that the ground state wave function is positive, which is not at all obvious well, from the first, except if you think of, let's see, one-dimensional problems. You know that Sturm-Liouville problems, that the lowest function does not have any nodes, but this is, of course, a considerable generalization of that. So the ground state wave function is positive. And this means that the function itself, well, of course, after possible multiplication by a constant, because the wave function is always only defined up to a phase. But the wave function itself, and not only its square, defines a probability measure. Usually think of the wave function and the square is something positive and the probability measure, but here one can think of the wave function itself as a probability measure. And then Elliott defines and studies something which is a sort of a correlation function for this probability measure. So he takes a limit of the many-body wave function here, moves, so to say, all the particles to infinity except 2. And then the assumption is that, that this is now depends only on difference. And moreover, that this tends to a constant at infinity. And this is the independence at large distances, which I call it ILD assumption. And quite generally, that if you define analogous functions in the same way by integrating of more variables, that then the n function will tend to the n-1 function when variables move. Okay, and now from this assumption and from the Schrödinger equation for the original wave function, Elliott derives a nonlinear differential integral equation. And he shows that this equation gives the first term for the ground state energy at low density. In fact, in a rather very natural and simple way, much simpler than later things, which of course I had to use where you did not use this assumption, but you had to use lots of other tools. In particular, he could derive that the energy has the asymptotic form of the leading term, which is proportional to rho A, and the so-called Li-Huang-Yang term, which was rigorously proved only last year by Jan Philip and Søren Fournier. Had been an open problem for a long time. Now, in two papers from 2019 and 2020, then Elliott has, together with Erika Lane and Jocelyn, refined the simple equation to more complex integral differential equations, but still with only 3 variables instead of the full n-body problems. And he has he called this equation the big equation and the medium equation. And with further simplification, they reduced to the simple equation. But these new equations, they pose very interesting mathematical problems. And moreover, they lead to very interesting conclusions. One can, for instance, prove that one has Bose-Einstein condensation, which satisfies Ogolubov's asymptotic expansion of the depletion of the condensate. And besides these 2 papers, he has also, together with Carl and Jocelyn and Markus Holzmann, who is a computational physicist, has studied these equations numerically, and they found excellent agreement with Monte Carlo calculations, not only for low densities, but remarkably also for intermediate densities. And here is this paper of the 4 people, which appeared now in Physical Review A in 2021. So I think that this shows how Elliott's ideas continue to be fruitful and inspire new results and pose challenges also for future generations. Now, I think I should now come to a conclusion, but I ask you to allow me to end on a personal note by repeating something which I said in an after-dinner speech in Princeton on the occasion of Elliott's retirement 3 years ago. I have had the good fortune to know Elliott well for more than 30 years and take part in several of his scientific enterprises. I regard it as a privilege to have known Elliott all these years and had the opportunity to interact with him and his wife, Christiane, not only on scientific matters, but also other things. In the beautiful home of Christiane and Elliott in Princeton, which is full of exquisite souvenirs from their wide travels all over the world, the 3 of us have had a countless conversation over dinner about politics, history, linguistics, art, literature, food, wine, and exotic countries and cultures. For me, this has been a precious gift. In the greatest of the Icelandic medieval sagas, the Njál saga, the 2 main protagonists are a wise man, Njál, and his younger friend, Gunnar. who regularly enjoys Njal's advice and support. On one such occasion, Gunnar says to Njal, "I appreciate your gifts, but even more, I value your friendship. I ask you now to join me in congratulating Elliot on the reception of the AC medal." Thank you.
Thank you, Jakob, for this very beautiful appreciation of Elliot's impressive work, and in particular for some personal recollections. Very, very nice. I enjoyed it very much, and I think everybody did so too. Are there any comments? Or I don't think that this is
Not
a typical
appropriate.
situation after a scientific talk, so maybe we can just.
Yes. I want to make a comment.
Yes, please.
Yes, I also want to say how much I admire Jakob and how much I value our association. Yes, I just wanted to reciprocate what Jakob said about our relationship. It really was, it still is, I hope, very intense, and I have learned so much from him. And many of the things I did would not be possible without his ideas and inspiration and encouragement, and the work we did together was very deep, a very deep part of my life. So thank you so much, Jakob.
Thank you again, Elliot.
Very good. Now the big moment has come, almost, because there will be some music now. Could I please ask you?
Oh.
So while they set up, let me introduce the two musicians. We have Elisabeth Zeisner on the cello and Wolfgang Augustin on the violin. And if the information I have is correct, they will play an invention by Bach. Yes, please. Thank you very much. Beautiful, very moving. Thank you. So we would like to award you the Medal of the Erwin Schrödinger Institute now. normally I would give you the medal, which is here. So the award comes with a medal and with a certificate. And let me show both the medal here and the certificate. I will share my screen. And let me first read again the citation. So Professor Elliot Lieb, I'm sorry, it's at University of Geneva, which is wrong, of course. This is from last year. Professor Lieb is honored for his deep and groundbreaking mathematical analysis of fundamental problems and models of many-body physics, foremost his works of recent years, which continue to be outstanding and inspiring to a new generation of mathematical physicists. Two highlights in the realm of Coulomb systems are a mathematically rigorous justification of the local density approximation in density functional theory and the proof of the equivalence in the thermodynamic limit of three different definitions of the minimum energy of a homogeneous electron gas. This is joint work with Mathieu Lewin and Seiringer. So, as I said, the ESI medal comes, of course, with the medal. I have the medal here, which is kind of hard to see for you, but I will show it here on my computer so that everybody can see it. So you see the medal here, the front and the back. The medal is designed by Philip Steinkellner, who is a graphic designer who did many things for the ESI. On the left, you can see here the front of the medal, Erwin Schrödinger in a pensive mood, and on the back you see the logo of the Erwin Schrödinger. So the medal is made of silver, made by a company in Tyrol. They have a long tradition in silver mining and minting there. There is also a certificate. I will show you the it has a citation. It's also designed by Philip Steinkellner and put it up in your office. Now, normally I would now shake your hands and give you the medal.
Shake hands.
And the certificate. We cannot do that. And on top of that, there is also some money that you will get, and I would like the ESI Association for contributing to the prize money. So I would give you all of that. Now I have to mail it, and the only thing that you will receive now is an applause from the audience. Congratulations, Elliot, for the ESI medal. It's really an honor for the medal that you are the second recipient of them. So now it's your turn.
All right. First of all, let me thank you, Christoph, and Jakob Yngvason for your very generous words, and which will not be forgotten. And let me thank also Professor Solovey and Philip and Seiringer, Robert Seiringer, for very beautiful lectures. I mean, they really were very beautiful. And I'm very glad that I believe this proceedings will be recorded and people will be able to hear your lectures because they were very clear. My thanks also go to Professor Lewin, Mathieu Lewin, and Robert for thoroughly enjoyable collaboration. Of course, there are many collaborators, but especially you two, because this is the joint work on which was cited for the ESI medal. So, but also should mention Jan Philip, which I already did, and Jakob for joint work. These were glorious collaborations, and they still are, I hope. It's a great honor for me to receive this award especially from an institution to which I've been associated since its inception about 3 decades ago. ESI came into existence through the hard work of several people, mainly Walter Thierry and Wolfgang Reiter. At a time long ago when scientists from the East badly needed much support. Times have changed a lot in this respect. But that was the original idea, and everybody should remember it. For the first 14 years after ESI's founding, I served on the Scientific Advisory Board, and I had the pleasure of seeing it grow into the Institute grow into one of the most important centers for the interaction of physics and mathematics. Under the leadership of Professor Thierry first and Michro, Yngvason, Schmidt, Schwärmer, and now Professor Delago. And an equally important and hardworking advisory board, now chaired by Professor Cvetic. And let's not forget that supporting this is a superb, dedicated secretariat, which I want to thank for their kind help over many years. So I trust that the government of Austria, as well as the government of the University of Vienna, will continue to appreciate the achievements of this institute and will continue to support it and help it continue to grow. It's a very important treasure that must be maintained. So thank you very much for this medal, and now I will give a little talk of my own. And I will try to do this, but it will, since I'm not very good at this kind of thing, it may take a little while, but here we are. And I will go to full screen if I can figure out. And let me see, no view, full screen. There we go. Is that good? Can you hear me?
We can hear you, but you need to share your screen.
I need to share the screen. I keep forgetting that. And now I forget this. I knew I would forget something. Let me see. How can I get, oh gosh, how do I get out of this thing? Exit full screen mode. Let me see. Wait a minute.
You need to share the screen with the little green button at the bottom.
Yeah, but I can't get to the bottom again because, wait just a second. Sorry. Ah, there we go. Green button. Ah, got it. Okay, so share. There we go. Is that, can you see this now? Is it shared?
No.
I have to go to the top now, right? Where do I go? Oh, the top doesn't show up.
So in the Zoom window, you could see.
Okay.
Yes, perfect. Now, if you go to
the view,
full screen view.
There we go.
Perfect.
Okay. Thank you so much for this delay. Thank you for your patience. So I was asked to give a talk, which I'm happy to do, and I had to think hard about what to talk about. And it's sort of a wide open thing, just say something. So I decided to talk about a theorem, which I did in 1983. It's published in Invenciones, if you want to look it up. This theorem is one of my favorites. So I hope you don't mind my sharing it with you. And it is very simple to state this theorem. Anybody can understand. I mean, there's no technical things necessary. But it does have some applications in mathematics, but they're very definitely in geometry. And physically, it has some interest too. It says something about the uncertainty principle. in a very strange way, but it is about the uncertainty principle. So since the audience is both mathematicians and physicists, I thought this might be appropriate. So let me start with an apology for plagiarizing the title of Mark Koch's famous 1966 paper, Can One Hear the Shape of a Drum? That became very popular for a while. For microwave cavity, for example. Now, the commonality between Koch's paper and my paper is the question, do the facts about the spectrum of the Laplacian, minus Laplacian, minus delta, in a domain omega, some domain in Rn, with Dirichlet boundary conditions, that's psi equals 0 boundary condition, does the spectrum tell us something interesting about the geometry of the domain? For example, the volume, the convexity, or whatever. Lots of things that the spectrum might tell you. And that's hence the title. Now, to avoid confusion, Katz's drum is a flat sheet. He's thinking of a two-dimensional drum. It's the sheet that's vibrating, and it's the frequency of the sheet that counts. My bass drum is a chamber in R3, like a closed organ pipe or a closed-off temple bell or a real bass drum, where the frequency is determined by not by the sheet is only a transducer. So, and my soccer ball is a real ball. It's not a disc. For Koch, the ball is a disc. For me, the ball is a ball, hence a soccer ball. And my theorem is relevant for all Rn, whereas Koch's is only talking about R2. And dimensions 1 and 2 for my theorem are not so interesting. The real action starts with dimension 3, which happens to be the dimension that we live in. So this talk will not be terribly long. I hope you're not too tired, so let me continue. It was discovered after some while that Koch's conjecture is not true. Some of it is true, but it's not really true the way stated, because we need some additional assumptions in 2 dimensions to really determine the whole shape of the drum, the whole domain. And those additional conditions might be, for example, a condition on convexity, like simple convexity, simple conductivity, I mean. And by now, there are many known pairs of 2-dimensional polygonal domains in 2 dimensions with identical spectra. And group theory played a big role in their discovery. I don't want to go into this, but it was hard work and it's some deep mathematics involved. The analog of Koch's conjecture in R1, one-dimensional system, just the second derivative, is trivially true. Since the only connected domain in 1 dimension is the line segment on line interval AB, and the length of this line determines the entire spectrum. Here is the spectrum in 1 dimension. So there can only be one kind of spectrum, and that determines the length. And that's the end of it. In fact, you only need to know the ground state, the lowest eigenvalue, and that determines everything. So 1 dimension is really boring. 2 dimensions is interesting, but rather complicated. So I am only interested in the smallest eigenvalue. Whoops, sorry. The so-called gravest mode, according to Lord Rayleigh, the lowest eigenvalue of my drum. And I'm trying to find out what one can determine from just thinking about the lowest eigenvalue of the drum. And I'm calling that lambda. Lambda is the lowest eigenvalue in the domain omega. What can I say about omega if I tell you the lowest eigenvalue? So this becomes now, if I tell you the lowest eigenvalue of the Schrödinger operator, what can you say about the shape of the drum, of the domain? And now Faber and later Kron independently proved that for a given volume, if I specify the volume of the domain, the ball has the smallest lowest eigenvalue. That's proved by a rearrangement inequality. And I'm not going to go into that, but the ball has the smallest, lowest eigenvalue given the domain. Well, put it another way around, if I give you the lowest eigenvalue, one has a lower bound on the volume, namely the volume of a ball with the same lambda. So the lowest eigenvalue tells you that the volume cannot be too small. Now that's good physics. That's the uncertainty principle right there, a Heisenberg uncertainty principle. So you can ask the question, if I tell you the lowest eigenvalue, does a comparably sized ball, we don't expect the whole ball to get in, but maybe a smaller ball might get in, half the size or something like that. Could we expect something like that to be true? And the answer is no. Definitely no. And that's the surprising fact. Until 1983, that was more or less what was known about the problem. No, you can't say anything about inserting a ball. End of story. So let me try to explain why it's so hard to say anything about a ball. So here's some ancient wisdom. For R1, the domain, of course, has to be an interval. There's nothing else. And 1 over the square root of lambda is the length of the interval. So the ball of this diameter, of course, nicely fits into omega. So in one dimension, the answer is yes, always. And it's the ball is the answer. You get the whole ball in. So the end of the boring R1 story, there's nothing to say that's very interesting there. For R2, given lambda, there is no lower bound to the radius of an inserted ball without some topological assumption. So in other words, the answer is sometimes yes and sometimes no, depending on what further topological assumption you want to make. For example, simple connectivity, for example. And the names are some of the names associated with this are Hyman and Asserman and Cheeger, Jeff Cheeger. So there's a literature on this. In R3, or n bigger than or equal to 3, the answer is no, period. Just you cannot do anything, and I will explain that. The reason the answer is no in 3 dimensions is that omega, your volume, you know something about the volume now. Remember, it's the order from, you can give a lower bound on the volume. So you know that. That's true. But after that, you can't say much else about inserting a ball, because I could have very many thin needles inside the domain. For example, needles sticking, the person who cast the bronze bell was sloppy, and he left things sticking out from the bell into the interior, and sort of needles, very fine needles. And these needles will deflate any soccer ball, if there are enough of them, just about. And you might want to, any soccer ball you might want to insert, yet change lambda very little. Why is that? Because in Rn, for n bigger than or equal to 3, a line, or a line segment, just a thin, a mathematically thin line, has zero capacity. Zero capacity. In 2 dimensions, a line has capacity, just as in 3 dimensions, a sheet, a metal sheet, in two-dimensional sheet in 3 dimensions has capacity. It has no measure, but it has capacity. You can put charge on a sheet, but you cannot put charge on a needle in 3 dimensions, an infinitely thin needle. So there could be some very, very thin needles sticking, a lot of them, sticking in, excuse me. So you could be very many thin needles sticking into the ball and into the domain and preventing, changing the lowest eigenvalue very, very little, but enough of them so that you can't stick any ball in, practically speaking. In other words, there exists a huge bass drum with an arbitrarily small lambda. You make the lambda as small as you like, into which even a golf ball will not fit. There's a way out. Hoffnungslos aber nicht ernst, as we say. So here's the theorem that I proved in 1983 about this. The idea that I had was, well, I cannot stick a ball in, but I think I can stick a fraction of a ball in. So let's do the following. Choose some fraction you like, your favorite fraction, say 60%. And I ask really if I can insert 60% of a soccer ball into omega. How much radius would this ball be? So I'm allowing, so this infinitely thin needles, these needles, but I fatten them out just a tiny little bit, so I don't change the measure inside very much. I don't change the lowest eigenvalue very much, but nevertheless, I have to change by thickening the needle, I have to give up a little bit of volume if I'm willing to get 60% of the soccer ball into there, well, maybe I can do this with a radius that we would expect would be 1 over the square root of the volume of the eigenvalue. So we expect that as this fraction goes from 0 to 1, the fraction that I pick, the radius of such a ball goes from the volume to the 1 over nth power. This would be the case if we didn't have the needles and we had a ball, to 0 as the fraction goes from 0 to 1, or 1 to 0, to 0 to 1, excuse me. Now, in the following theorem, and the rest of this talk, I omit all dimension-dependent geometric constants. For example, in this talk, 2 pi equals 1. And as I tell my students when I give a course in mathematical physics, or physics, even real physics, I tell them in this course, 4 pi also is equal to 1. These are universal units. Okay, so modular geometric constants, the following is true. So you choose the fraction phi that you like, and I will denote BR, ball in Rn of radius R. That's what BR is, just a ball of radius R. And its volume is R to the nth, of course, in these units. Now, let omega be a domain in Rn with lowest eigenvalue lambda. Define the radius, a radius, special radius, in the following way: lambda times r squared. You see, we expect the radius to be inversely proportional to the square root of this eigenvalue. So let lambda times r squared, whatever lambda might be, I define r by setting this equal to phi to the minus 2 over n minus 1. This is a positive number since phi is less than 1. In that case, BR, the ball, the radius, this R, can be translated on top of my domain so that the volume of the ball inside the domain, which is what's here, is at least equal to the fraction of the volume of the ball, the stated fraction. I can turn this around this equation and view this from a different perspective. I can say, given R and given lambda, define phi this way. I can always do that. This is the definition now of phi. I can get, let's say, phi, solve this equation, and phi turns out to be 60%. Then I say, you chose R, I can get 60% of that ball into my domain. Guaranteed. So that's the theorem of 1983. That you can get a fraction of the ball in. Maybe I should ask if anyone has any question, or maybe it's not so easy to. I hope this is clear. But just imagine a picture. There's a domain of some kind. It's got a lowest mode. The lowest mode may be very low, but I cannot fit a ball in because of meters. But I can get 60% of a ball in. How big is the ball? So when I make the radius smaller and smaller until it becomes a golf ball, the phi goes up to 1. Namely, that as the ball gets smaller and smaller that I demand, then the fraction of this golf ball gets bigger and bigger and closer to 1. So I can view it that way. So, example, if omega is in R3, this is domain, and the eigenvalue is, for example, the eigenvalue of a ball of radius 1, but omega is full of ultrafine needles, I am nevertheless able to fit 60% of a soccer ball of radius 1.5 into omega. That's the theorem. So this changed the game in 1983. Now, this basic theorem this theorem that I just met, theorem 1, is actually a corollary of a surprising theorem. It's a very simple theorem. It says the following, theorem 2. I take two domains, I call them omega 1 and omega 2, in Rn. Any dimension you like. Then I can translate one, without rotation. I don't even need rotation here, although rotation would make my job easier, but I don't need it, just translation. I can translate omega 1 only, that is, without rotation, so that it's the eigenvalue, the lowest eigenvalue of this intersection is less than or equal to the sum of the eigenvalues of the original domains that I started with. That's the basic theorem. And it's surprising, but it's true. And I will give the proof even. Now, here's some remarks about this. First of all, I could apply, this is also true for W1P eigenvalues. Mathematicians, analysts will understand what these eigenvalues mean. I will not explain it, but it works for that too. The proof is so simple. In order to prove theorem 1, which is back here, I take omega 1 in this theorem 2, I take that to be the domain of interest, and omega 2 to be a ball of radius r. Which r? Well, that r defined up there. And when I play with this and use the fact that the volume, this isoparametric inequality, that the ball has the lowest eigenvalue given the volume, and I leave that to you as an exercise, it's really very simple. You don't need anything, just use what I said here and together with this statement, and out comes theorem 1. Now, theorem 2 is sharp. in the following sense. If I take omega 1 to be an infinite slab of thickness A, I hope everybody understands. Let me think of a slab of steel coming out of the steel mill. And the thickness of this infinite slab is A. And omega 2 is another slab of thickness B. But the orientation of omega 2 relative to omega 1 is that they are perpendicular slabs. So that I hope that's clear what that means. The two slabs are sitting on top. One slab is sort of cutting through the other slab. So the intersection of the two is what? It's a little rectangle times infinity in the other two, n minus 2 directions. So if I have that, then the lowest eigenvalue for omega 1 is just pi over a squared for a single slab. It's infinitely big, remember, so no edge effects. And the lowest eigenvalue for omega 2 is pi over b squared, and the intersection is just the lowest eigenvalue for this little rectangle, which is pi over a squared plus pi over b squared, which is the sum of the eigenvalues. So that's the example. And as I rotate the one slab relative to the other, I can get them both parallel, and then this inequality becomes worse and worse and worse. I mean, so in that sense, theorem 2 is sharp. It really does happen. So that's theorem 2, very simple theorem. And now I will give you the proof of theorem 2. And at this point, feel free to go to sleep. But it's really short. It's only this one slide, and then we'll be done. It's really a very short proof. So let psi1 of x and psi2 of x be the lowest eigenfunctions. I didn't put lowest here, the lowest eigenfunctions of omega 1 and omega 2. I have two domains, and those are the eigenfunctions with Dirichlet boundary conditions, and lambda 1 and lambda 2 are the eigenvalues. Now, if I look at psi1 of x minus y is just some vector in Rn, that's the as a function of x with y fixed. It's an eigenfunction for omega 1 and y, which is the translate of omega 1 by y. That's the ground state for the shifted domain 1, omega 1. Good. Now I'm going to define a variational problem for the intersection of the domains. And my variational function is going to be, well, what else should it be? It's the product of the eigenfunctions for the two domains. Here it is. This is the first domain shifted by y. That's the second domain. I take the product, and this product has the property that it has the right boundary conditions. That is, it hits zero. It's zero if either one of these guys is outside of its respective domain, which is outside of the intersection. So it really satisfies the boundary conditions. It's a perfect. That is, I define, if you like, psi1 and psi2 to be zero outside of their respective domains, which I'm allowed to do in H1. Okay, now I want to tell you that for suitable y, taking this f as a variational function for the intersection of the two domains in question, for suitable y, this guy will have an eigenvalue that's less than or equal to the sum of the eigenvalues. Then we're done. So what I'm going to do is write the variational principle in a slightly different way than it's normally written. And I'm writing it in the following way. This is the kinetic energy, if you like, the Dirichlet energy or whatever, of this function f, minus f Laplace with respect to x of f dx. That's the kinetic energy. That's a positive thing. And this guy is what would be the denominator if I use the usual Rayleigh-Ritz principle, but I'm writing it as a sum. And in order to prove that the lowest eigenvalue of the intersection is less than what I said, less than the sum. And what I'm trying to say is that this integral divided by that integral is less than or equal to lambda 1 plus lambda 2. That is that this thing, for some y, this integrand is negative. That's just another way to write it. But I want to write it in this linear form instead of a ratio. Why do I want to do that? Because I want, in order to prove that this can be made negative with this fixed, I mean, I could have said it the other way, but it's easier to do it. In order to prove that this can be made negative for some y, I look at its integral and I prove it's 0. And I know that someplace it's positive, that if they're partially overlapping, this is positive, somewhere it's negative. This integrand is not 0 everywhere, that's for sure. Well, if it is, that's fine too. But the integral, but it won't be. So if its average is 0, then somewhere it's negative for some y. And that will end my proof. And not only will it prove that for some y, but it will tell you that for a set of positive measure, it's true. Positive measure of y's, lots of y's, it's true that this combination is negative. So now we are done. I now calculate. I have to calculate this Laplacian here on Fy. Remember what Fy is, it's this product. So when I calculate minus Laplacian of Fy, there will be 3 terms that I get. Everybody, this is calculus 101. First, there's this minus Laplacian of psi1 times psi2. Then there's, and that, of course, is lambda 1 times psi1, this guy, so that's lambda 1 times f. Okay, because that's f. The second term is when I hit the Laplacian hits the psi2. And for the same reason, I get lambda 2 times f, because I got a lambda 2 out of this. Okay, so these 2 terms together just cancel this term here. Now the third term, that better turn out to be negative sometime. Or at least 0, I will turn out to be 0 when I integrate it. And what is that? That's the cross term. I get the gradient of psi1 times the gradient of psi2. That's with a 2 in front of it. Which is twice the gradient of respect to x is minus the gradient with respect to y. The gradient of this guy with respect to x is minus the gradient with respect to y. So I write it this way, times the gradient. Now, here, as I said, the alpha plus beta terms exactly cancel this. And now we're left with this. Now, notice that this combination here, when I multiply it by Fy, Fy is what, psi1 times psi2. This is the gradient with respect to this bit, is the gradient with respect to y of this object squared. That's what that bit is. And this one is the gradient of psi2. Now I will change orders of integration and integrate dy first. So what do I get? Well, this is a gradient. So for any x, this integral is 0 dy. And so when I integrate dx, I get 0. And I prove what I want to do, that this average over y is 0, so somewhere it's negative. And which means that somewhere, for some y, the eigenvalue is less than than the sum, and that's what I set out to prove. And so that's the end of the story. And thank you for listening.
Thank you, Elliot, very much for the kind words about the ESI and also for your talk. Are there any questions or comments to the scientific part of his talk? Doesn't seem to be the case. Everybody is stunned. So I guess then I would like to ask the musicians to play another piece. Thank you very much. Beautiful again. You recognized it, Mozart, eine kleine Nachtmusik. So this concludes our ceremony. Let's congratulate Elliot again for the ESI medal. I would like to thank you for attending here in the lecture hall and out in the internet. Take care, stay healthy, and I hope to see everybody at the ESI again soon. Thank you.